Earth is a silent stage of new beginnings. For hundreds of millions of years, life has emerged, flourished, and nearly been erased. In long cycles, almost imperceptible to the human scale, our planet has gone through moments when biological diversity was crushed by forces so immense they seem mythical. These are the so-called mass extinctions. But what exactly defines a mass extinction? Why are some events classified as such while others are not? What is the true scale of destruction involved? In this first dive, we need to fully grasp the meaning and actual dimension of this concept, one that carries both scientific weight and existential magnitude. A mass extinction is defined by an abrupt and global reduction in biodiversity on a planetary scale, occurring within a geologically short time frame. In practical terms, this means that over 75% of all living species may vanish in less than 2 million years, a blink of an eye on the geologic timescale. This is not an isolated or regional disappearance, like when a species becomes extinct due to local causes, but rather a profound biological crisis involving trophic collapses, destruction of ecological niches, and a complete reorganization of life on Earth. These extinctions affect not only large animals, but also microorganisms, plants, insects, corals, birds, reptiles, every living being that forms the fabric of the biosphere. The first modern attempt to systematize and identify these extinctions came from the study of fossils. Paleontologists like Georges Cuvier and later Jacques Sepkoski noticed that when observing deep geological layers, certain fossils would abruptly disappear from one epoch to another, as if life had suffered violent interruptions. This observation led scientists to map the major biological crises in the history of the planet. With the advancement of stratigraphic geology, radiometric dating, and paleobiology, it became possible to identify at least 5 major mass extinctions over the past 540 million years, a span known as the Phanerozoic Eon, representing the age of visible fossils. These 5 great extinctions, Ordovician, Devonian, Permian, Triassic, and Cretaceous, not only erased species, but also reshaped the path of life. In each of them, dominant forms vanished, making way for new evolutionary groups to rise. Dinosaurs, mammals, birds, bony fish, even flowering plants. All of them emerged or expanded in the aftermath of these ecological collapses. Life, after each fall, began again with a new architecture. But each new beginning came at a steep price. After every mass extinction, it took millions of years to restore previous levels of diversity. And even then, the world never returned to what it was before. The causes of mass extinctions are varied, but they share a common pattern. They involve extreme environmental disruptions, large-scale volcanism, giant asteroid impacts, drastic sea level changes, sudden shifts in global climate, ocean acidification, methane explosions, collapses in photosynthesis. Even distant supernovae may be involved. In some cases, extinctions were triggered by a combination of factors in a domino effect. For instance, a massive volcanic eruption might release gases that amplify the greenhouse effect, alter the climate, and reduce oceanic oxygen levels, impacting the entire food chain. These cascading effects are what make mass extinctions so deadly and irreversible. Another important aspect is that mass extinctions are not instantaneous in human terms. Even the most rapid ones may have lasted hundreds of thousands of years, which is still considered abrupt on the geologic timescale. Therefore, when we talk about mass extinctions, we are dealing with deep global processes that shape the destiny of the biosphere on timescales far beyond our perception. It's as if Earth breathes slowly and from time to time exhales so deeply that it wipes almost everything away. Today we know that Earth has gone through dozens of extinctions, some minor, others catastrophic. But it is within the great mass extinctions that we find the true milestones in the history of life. These events are so profound that they officially mark the end of one geologic era and the beginning of another. They serve as entire chapters in the planet's long encyclopedia. And more than that, they are also a warning. Life is resilient, but not invincible. A mass extinction is a reminder that Earth, although alive, does not guarantee permanence to any species, not even the most adaptable. The question that echoes through every extinction is always the same: who survives and why? In this script, we will journey through all these great extinctions, uncover their triggers, examine the fossils left behind, the worlds that were erased, and what rose from the ashes. Each chapter will lead us through a collapse and then a resurrection, a journey through Earth's deepest scars, where the death of some has always meant the rebirth of others. Earth's history is not told in days, months, or years. It is narrated in phantom millions and billions of years, in eras and periods that stretch across spans so vast they defy our imagination. To understand mass extinctions, we must first grasp this deep time, a pulse that moves differently, almost as if the planet breathes in vast, silent cycles. This geological time is the stage where life emerged, spread out, dominated oceans, skies, and continents, and was also brutally interrupted on multiple occasions. In this time, extinction is not an accident, but part of the very rhythm of existence. Earth is about 4.5 billion years old, and for almost all of that time, life was microscopic, invisible to the naked eye. Only in the last 600 million years, a period called the Phanerozoic, did complex multicellular life forms begin to leave consistent fossil records. Evolution, in this context, is an incredibly slow process, driven by mutation, natural selection, and adaptation to constantly changing environments. Species emerge, diversify, dominate ecological niches, and eventually disappear. Extinction, therefore, is not an anomaly. It is the final destiny of most species. It is estimated that over 99% of all life forms that have ever existed are now extinct. But while normal extinction occurs over millions of years, gradually replacing species, mass extinctions break that natural rhythm. They are abrupt accelerations in the disappearance process, as if life's clock were suddenly shattered, fast-forwarded by a blind, colossal force. Instead of vanishing slowly, entire species are wiped out in clusters. Whole ecosystems collapse simultaneously. Food chains fragment, and when chaos takes over, only those with luck, biological flexibility, or extreme survival traits manage to endure. Earth's timeline is divided into eons, eras, periods, epochs, and ages, units of time that help geologists organize planetary history. Most of the major extinctions we'll explore took place during the Phanerozoic eon, specifically within the Paleozoic, Mesozoic, and Cenozoic eras. Each of these eras witnessed at least one major mass extinction. At the end of the Ordovician, around 443 million years ago, marine life was devastated by abrupt climate change. At the end of the Devonian, 372 million years ago, marine chains collapsed gradually. During the Permian, around 252 million years ago, nearly everything vanished. In the Triassic, 201 million years ago, another collapse cleared the path for the dinosaurs. And finally, 66 million years ago, an asteroid sealed the end of the reign of giant reptiles. These dates, seemingly remote, mark crucial turning points. At each one, life passed through a bottleneck, a reduction in diversity so severe that only a few lineages survived. And it is thanks to those unlikely survivors that we have today's animals, plants, and even ourselves. For example, mammals only had a chance to thrive after the extinction of the dinosaurs. Flowering plants emerged shortly before the Cretaceous collapse. Bony fish, ancestors of terrestrial vertebrates, made it through the Devonian. Every major evolutionary step is connected to a void left by a prior crisis. Earth doesn't just eliminate, it also creates space for reinvention. It's important to note that evolution is not a straight line toward complexity or perfection. Contrary to popular belief, life's history is full of broken branches, abandoned paths, biological failures, and experiments that didn't succeed. Some organisms were incredibly successful for tens of millions of years, only to disappear suddenly. Trilobites, ammonites, graptolites, stromatoporoids, all dominant in their eras, are now just fossilized memories. Mass extinction, in that sense, is like a forced pruning of the tree of life, cutting off entire limbs and leaving only a few sprouts to restart. When we study fossils, we realize that each layer of sedimentary rock is a more frozen chapter of time. The deepest layers hold the oldest records, and as we ascend, we find signs of catastrophic events. Dark layers rich in iridium, tsunami markers, signs of anoxia, gaps in fossil presence, and sudden appearances of new species just above. It's as if Earth left scars, tangible traces of past tragedies, and these scars, carefully read by geologists and paleobiologists, help us reconstruct every collapse, every recovery, every cycle of destruction and rebirth. Life at its core is incredibly resilient, but what we see in deep time is that resilience does not mean immortality. Not even the most well-adapted species were spared by the great extinctions. Geological time has no haste, but also no mercy. What it teaches us is that permanence is an illusion, and that every era, no matter how grand, will one day come to an end. In this script, we will traverse this deep time like explorers of a silent world. We will look back not with nostalgia, but with reverence, because understanding the past also means understanding the present and anticipating the risks of the future. Earth's surface may seem stable when viewed from above, but beneath our feet lies a dynamic, ancient, and ever-moving system, the tectonic plates. These immense slabs that make up the Earth's lithosphere slowly drift atop the planet's viscous mantle, driven by convection currents fueled by Earth's internal heat. Over millions of years, these plates collide, split apart, dive beneath one another, and rearrange themselves, reshaping landscapes, opening oceans, forming mountains, and unleashing silent destruction. Plate tectonics not only shape continents, but also play an active role in the mechanisms behind mass extinction. Each time plates crash or drift apart, they trigger a chain of deep effects. When they collide, they form mountain ranges like the Himalayas. When they separate, they create mid-ocean ridges where new crust is formed. But the most critical events happen when one plate dives beneath another, a process called subduction. In these zones, friction and extreme heat generate intense volcanism, capable of ejecting millions of tons of carbon dioxide and sulfur into the atmosphere, drastically altering the global climate. When eruptions of this kind occur on a massive scale, they're called in-flood basalt events, true geological extinction-level phenomena. Earth's history records multiple instances of such colossal eruptions. At the end of the Permian period, for example, the Siberian traps. Vast volcanic formations in present-day Russia erupted over hundreds of thousands of years, releasing staggering amounts of toxic gases. The result was global overheating, ocean acidification, and a collapse in marine oxygen levels. This event coincides with the most devastating extinction ever recorded, in which over 90% of all species were exterminated. The connection between plate tectonics, volcanism, and extinction is now a well-established field within evolutionary geology, but the plate's role extends beyond volcanism. The rearrangement of continents impacts patterns of oceanic and atmospheric circulation. When continents merge into supercontinents like Pangaea, the available coastline decreases, along with it, the shallow marine habitats that are the richest in biodiversity. The formation of Pangaea at the end of the Paleozoic era is directly tied to the Permian extinction, not only due to volcanism but also because of the climatic and ecological consequences of that continental fusion. The opposite is also true. When supercontinents fragment, they create new seas and currents that redistribute nutrients and foster evolutionary booms. Another tectonic factor is the vertical rise or fall of continental regions. Areas that are now arid deserts were once covered by tropical seas. Vertical movements of the crust can turn wetlands into dry plains or cause fertile lands to be swallowed by the ocean. When these shifts happen on a large scale, they contribute to local extinctions, and in times of crisis they can intensify global patterns. The loss of habitat, especially in shallow marine zones, is one of the most frequent causes of marine species disappearance throughout geological history. Tectonic plates are also linked to earthquakes and tsunamis, which, while not direct causes of mass extinctions, serve as symptoms of the planet's dynamism. A megaquake can cause localized destruction, but rarely disrupts biological balance on a global scale. However, when combined with volcanism, climate shifts, and ocean acidification, their effects add up in waves of instability that weaken ecosystems to the point of collapse. In studying mass extinctions, it's essential to remember that nothing happens in isolation. Tectonic events act as catalysts. They trigger the changes, and those changes, cascading, reshape the world into something hostile. That's why many scientists refer to mass extinction as death by 1,000 causes. Plate motion may be the finger that pulls the trigger, But the full disaster involves the weapon of ocean chemistry, the bullet of climate, and the vulnerable body of the biosphere. Finally, the most chilling realization is that this system is still active today. Earth's crust still shifts, volcanoes still breathe gases from the mantle, and continents are still on the move. The planet has never stopped. And though today we live in a relatively stable phase, the same forces that once destroyed entire ecosystems remain silently at work beneath us. In its geologic dance, Earth has already wiped out almost everything more than once, and perhaps one day it will again. Before the dinosaurs, before even complex land plants, the planet had already witnessed a profound and global biological collapse. This event is known as the Ordovician Silurian extinction, the first major mass extinction in Earth's history, which occurred about 443 million years ago. It marks a turning point in marine life history because at that time, nearly all biodiversity was confined to the oceans. Primitive fish, trilobites, brachiopods, graptolites, algae, and sponges formed vibrant ecosystems in shallow seas, while land remained almost lifeless, a barren, rocky desert. During the Ordovician period, the planet experienced a phase of relative climatic stability. The seas were warm, nutrient-rich, and extremely biodiverse. It was a time of ecological expansion, with many marine groups flourishing in abundance. However, this calm was suddenly interrupted by a swift and deadly climatic shift. The primary trigger of this extinction is believed to have been an intense and abrupt ice age, caused by a drop in atmospheric carbon dioxide levels. This sharp decline in CO2, likely related to global cooling and continental drift toward the South Pole, led to a planetary freeze with catastrophic consequences. As the climate cooled, vast ice sheets formed over the supercontinent Gondwana, which was then located near the South Pole. The growth of these glaciers caused sea levels to drop drastically. Millions of square kilometers of shallow continental shelves, where most marine biodiversity thrived, were exposed, drying out entire habitats. This sea level fall destroyed the richest life zones, leading to mass death among species unable to migrate or adapt. Trilobites, bryozoans, graptolites, and various mollusks were especially affected. This first phase of extinction was followed by a second shock, the end of the Ice Age, and a sudden return of global warming. The melting glaciers poured vast amounts of fresh water into the oceans, altering salinity, temperature, and oceanic circulation. This climatic reversal placed additional stress on ecosystems already weakened, resulting in a second wave of extinctions. Altogether, it is estimated that about 85% of all marine species vanished during this double event. It was a global, devastating impact, but a silent one. There were no explosions or craters, just the slow force of cold and heat. Despite its magnitude, the Ordovician Silurian extinction was long overlooked. That's because the affected species left behind small, often microscopic fossils, which don't draw as much attention as dinosaur skeletons. However, its importance is colossal. It was the first major collapse of the biosphere, leaving deep scars in the ocean's ecological structure. This event shows that even gradual changes in global climate can trigger biological catastrophes, especially when they occur within short spans of geologic time. The fossils from this period reveal a world in transition. After the extinction, the Silurian period gave rise to new biological groups and more resilient forms of marine life. Corals, jawed fish, and primitive plants began to diversify, filling the niches left behind. As always, life survived, but it was forever changed. The Ordovician Silurian extinction marks the beginning of a pattern that would repeat many times, a planetary trauma followed by evolutionary rebirth. This episode also raises a crucial question for our time. If a simple change in atmospheric carbon dioxide was enough to cause a global collapse 443 million years ago, what will happen now that CO2 levels are at record highs, driven by human activity? The first mass extinction serves not just as a historical lesson, but as an ecological warning. Earth has already shown what climate can do when balance is lost. The Ordovician Silurian extinction is, therefore, the starting point of a story of loss and resilience. It reminds us that even on a young planet, life was already facing the unstable forces of geology and climate. Earth has never been an easy home, and surviving it has always required more than adaptation. It has demanded endurance through violent, brutal, and unforgiving change. Imagine an entire planet covered in white. Not just the poles, not just the mountain ranges, but every continent, every ocean, every tropical plain wrapped in ice and snow for thousands or even millions of years. A globe without open seas, without liquid rain, without green, without a normal carbon cycle. A silent, inhospitable planet glowing under a pale light. This extreme vision is the basis of one of the most dramatic theories in Earth's climate history, the so-called snowball Earth hypothesis, a scenario in which the planet was literally transformed into a frozen sphere, with catastrophic impacts on life. The snowball Earth hypothesis emerged to explain geological evidence that defied conventional climate logic. Glacial rocks have been found in present-day equatorial regions like the Congo, Australia, and the Amazon. These deposits date back to the Kansas Cryogenian period, between 720 and 635 million years ago, well before the 5 officially recognized mass extinctions. For such ice to have formed so close to the equator, it would mean that the entire surface of the planet was covered in sea ice and continental glaciers, even in tropical regions. The conclusion was radical. Earth had undergone one or more total ice ages in which the climate system had collapsed entirely. According to proponents of the theory, this global freeze may have been triggered by a combination of the drastic drops in carbon dioxide, reduced solar activity, and changes in surface reflectivity. As glaciers grew and temperatures fell, more sunlight was reflected back into space, creating a feedback loop that accelerated the freeze. The more ice, the colder it got, and the colder it got, the more ice formed. In a short geological time span, the planet plunged into a deep glacial state, with oceans capped by an ice crust dozens of meters thick. For the life forms of the time, mainly algae, cyanobacteria, and simple marine microorganisms, this event was devastating. Photosynthesis plummeted, nutrient cycles collapsed, sunlight barely penetrated the icy ocean layers. Earth, now silent and white, had become nearly sterile. Only the hardiest life forms, adapted to extreme conditions, survived. Some scientists suggest that hydrothermal vents in the deep ocean may have served as the last refuge, providing enough heat and chemical energy to sustain small microbial populations through the freeze. But how did Earth escape this frozen nightmare? The answer may lie in its geological heart. Even under an icy shell, the planet remained active inside. Volcanoes continued to emit carbon dioxide, methane, and other greenhouse gases. With no rain or vegetation to remove this CO2 from the atmosphere, it accumulated over millions of years. Eventually, levels became so high that the greenhouse effect overpowered the ice's reflectivity. Global temperatures surged, and as abruptly as it had frozen, Earth thawed. This triggered the opposite kind of climate collapse: overheating, violent storms, and widespread erosion. Oceans warmed, oxygen levels rose, and life re-emerged with renewed vigor. Snowball Earth isn't directly linked to the 5 major mass extinctions, but it may have been the greatest biological bottleneck in history, an almost complete global extinction at a time when life was just beginning. If the theory is correct, and it remains hotly debated in scientific circles, then everything we know today exists only because a few resilient microorganisms survived the far-frozen planet. The evolutionary impact of this episode runs deep. After the thaw, the first fossils of more complex multicellular organisms begin to appear. It's as if the freeze had reset the game of life, forcing organisms to discover new strategies, open new biological forms, and reorganize themselves. The famous Cambrian explosion, which took place about 100 million years later, may have been partially driven by the ecological restructuring sparked by these extreme glacial ages. Earth didn't just recover, it reinvented itself. What the snowball Earth theory shows us, above all, is that the Earth's climate system is deeply unstable and capable of brutal extremes. It can freeze for millions of years, heat up in just a few tens of millennia, and make life swing from near extinction to breathtaking diversity. Climate is not just a backdrop for life, it is the stage itself, the director, and sometimes the villain. Understanding these extreme cycles is key to grasping the limits of the biosphere, and just how fragile the balance we now take for granted truly is. If today the oceans are the cradle of vibrant life, with colorful schools of fish, pulsing reefs and swift predators, we must remember that this biological richness has deep roots in a distant time, the Ordovician, also known as the Age of Fishes. Between 419 and 359 million years ago, Earth's seas were ruled by extraordinary creatures. Primitive sharks, armored fish, giant swimmers with monstrous jaws. It was during this time that the first vertebrates began to explore the edges of water, rehearsing their first steps toward dry land. But at the end of this glorious period, something terrible occurred. A slow and persistent collapse that wiped out 3/4 of all marine species. This was the late Devonian extinction event, one of the most mysterious and prolonged ecological tragedies in Earth's history. Unlike other mass extinction events, the Devonian collapse did not happen suddenly. It spanned nearly 20 million years, with multiple pulses of ecological crisis. Instead of one identifiable catastrophe, the late Devonian was a sequence of environmental breakdowns, as if the biosphere were being slowly suffocated. The most affected were the marine organisms that lived in reefs: stromatoporoid sponges, tabulate corals, trilobites, and mollusks. Many of the giant fishes that had once ruled the seas also disappeared gradually, giving way to smaller, more discreet and adaptable forms. But what caused this prolonged collapse? Science continues to debate the exact triggers, but leading hypotheses include massive volcanic eruptions, sea level fluctuations, global climate changes, and episodes of oceanic anoxia, that is, oxygen loss in deep waters. During the Devonian, vast primitive forests began to emerge on land, absorbing large amounts of carbon dioxide and releasing nutrients into rivers. This nutrient flow into the oceans may have triggered algal blooms and microbial explosions, which, upon decomposition, consumed the oxygen in the water. This phenomenon, known as eutrophication, turned vast marine regions into dead zones, literally oceans without air. With less oxygen, marine life came under immense stress. Large predators vanished, food chains collapsed. Once vibrant reef environments gave way to underwater wastelands. Anoxia spread through entire ocean layers like a suffocating blanket. Acidification and concurrent climate shifts completed the disaster. Earth was changing, and the Devonian marine life couldn't keep up. There is also evidence suggesting meteorite impacts during this period, such as the Siljan crater in Sweden, although these events are considered secondary contributors. What stands out about the Devonian is that the extinction had no single cause. It was the result of multiple pressures acting over millions of years. A carving silent extinction, insidious and prolonged, that slowly drained the oceans of life. Though less well known than the asteroid that killed the dinosaurs, the Devonian extinction had profound consequences. By eliminating many of the giant vertebrates, it cleared the way for the rise of the lobe-finned fishes, the direct ancestors of the first tetrapods, vertebrates that walked on land. It was in the ecological vacuum left by the collapse that life found unexpected new paths. From the aquatic survivors came much later the first amphibians and reptiles. In other words, had this extinction not occurred, terrestrial animals, including humans, might never have evolved as we know them. The Devonian also warns us about a phenomenon still present today: oceanic anoxia. Modern dead zones, like those in the Gulf of Mexico, are growing each year, driven by human activities, agricultural runoff, and global warming. What began as a prehistoric crisis fueled by natural shifts is now re-emerging with an anthropogenic signature. It shows that oceans have limits, and when we push them beyond their self-regulating capacity, collapse isn't just possible, it becomes inevitable. In short, the Devonian event was a slow, painful fall full of lessons. It reveals how an apparently stable ecosystem can crumble under multiple imbalances, and how life, even under extreme pressure, always finds escape routes. The great fishes of the Devonian disappeared, but they left behind a seed that would eventually take root on solid ground. A high price paid for the next phase of evolution. Imagine a volcano. Now multiply its power by 1,000. Picture not just a mountain erupting, but an entire continent spewing lava, gas, ash, and death for hundreds of thousands of years. An event so massive and prolonged that it altered the global climate, poisoned oceans, darkened the sky, and sealed the fate of nearly all life on Earth. This scenario, which sounds like something out of brutal geological fiction, is real. It happened at the end of the Permian period, around 252 million years ago, and became known as the Siberian Traps event, possibly the largest volcanic episode in Earth's history and the primary cause of the greatest mass extinction ever recorded, the so-called Great Dying. The Siberian Traps are a vast field of basaltic rock, located in what is now Russia, covering more than 2 million square kilometers. This colossal area was formed by uninterrupted volcanic eruptions that released trillions of tons of lava and gases into the atmosphere over a span of between 500,000 and 1 million years. These eruptions weren't explosive like the ones we see today, but rather massive basaltic lava flows, coating the surface with searing magma rivers that spread across hundreds of kilometers. But what most concerns scientists, even today, wasn't the lava. It was the gases released alongside it. These eruptions expelled into the atmosphere catastrophic amounts of carbon dioxide, CO2, methane, CH4, and sulfur dioxide, SO2. CO2 and methane intensified the greenhouse effect, abruptly warming the planet. Sulfur dioxide, reacting with atmospheric moisture, created acid rain that destroyed forests, acidified oceans, and corroded entire ecosystems. The combination of these effects led to extreme global warming, rising ocean temperatures, oxygen loss in marine waters, and the collapse of the marine food chain. It was a cascade of destruction. The sky, the sea, and the land became uninhabitable all at once. The result was devastating. About 96% of all marine species vanished. On land, 70% of vertebrate species went extinct. Entire forests burned or died from a lack of nutrients and water. Corals, mollusks, trilobites, groups that had survived previous extinctions, were wiped out with no descendants. The world quite literally stopped breathing. In many regions, atmospheric oxygen levels dropped so low that only the hardiest organisms managed to survive. The planet became almost lifeless, a terrifying pause in the fabric of life. Evidence of this catastrophe is found in geological layers across the globe. Dark layers rich in organic carbon indicate zones of oceanic anoxia. Long gaps in the fossil record reveal a world devoid of life for millions of years. Altered carbon and sulfur isotopes show a planet in chemical chaos. All of it points to a scenario in which Earth became nearly uninhabitable, without any asteroid impact, only through the relentless force of its own geological interior. It's important to note that the Siberian Traps were not an isolated event. Similar, though less extreme, episodes have occurred at other times and are also linked to mass extinctions. The Deccan Traps in India are associated with the Cretaceous extinction. The Columbia River basalts in the United States are more recent and less destructive. These examples show that the planet holds within it a potential for destruction as dangerous as any celestial body. Large-scale volcanism is one of the most powerful and unpredictable mechanisms in Earth's geodynamic system. And yet, there's an even more unsettling point. The recovery after the Great Dying was extremely slow, CETA. It's estimated that Earth's biodiversity took over Sassin's 10 million years to rebound. Even the surviving organisms were weakened, and evolutionary recovery was marked by lingering imbalances. Simple ecosystems dominated for a long time. Only much later did life begin to diversify again, paving the way for the dinosaurs, who would not appear until the following period. The Siberian Traps are, therefore, a brutal reminder that life on Earth has always depended on the delicate balance between the surface and what pulses beneath it. When that balance breaks, the consequences are absolute. In that moment of history, Earth became its own worst enemy. And the most striking thing is that this force still exists, dormant but alive, beneath our feet. Around 252 million years ago, Earth experienced an event so deep, so widespread, and so destructive that scientists simply named it the Great Dying. This is no rhetorical exaggeration. It accurately describes the largest mass extinction ever recorded in the planet's history, a global collapse that wiped out over 90% of all marine species and about 170% of terrestrial species. No other extinction came so close to erasing the entire tapestry of life. It was a true ecological reset, a point of near no return, that forever changed the course of biological evolution. The end of the Permian period was marked by a rare convergence of disasters. As discussed in the previous block, the Siberian traps released colossal amounts of carbon dioxide and methane into the atmosphere, triggering severe global warming. Average temperatures rose between 6 and 10 degrees Celsius in just tens of thousands of years, an alarming pace on a geological timescale. But heat alone wasn't the only executioner. The planet entered a state of total climate collapse. Acid rain destroyed vegetation, erosion washed nutrients into the oceans, and algal blooms consumed the remaining oxygen. The seas turned into bound-to-dead zones, dominated by hydrogen sulfide-producing bacteria, a toxic gas that may have spread into the atmosphere, affecting terrestrial life as well. Marine life was hit especially hard. Corals, brachiopods, echinoderms, trilobites, all were virtually eliminated. Entire food chains vanished. Plankton and microscopic organisms, the foundation of marine life, collapsed. With the ecological base shattered, neither apex predators nor intermediate species could survive. Fossils from this time reveal a sterile interval, where for millions of years there is little to no evidence of complex life. It's as if the planet had switched off its own biology, plunging into a deep silence. On land, the picture was just as grim. Tropical forests were devastated. Synapsid animals, the ancestors of mammals, were decimated, with only a few small nocturnal and burrowing lineages surviving. Most large reptiles and amphibians also vanished. Soils were depleted, the atmosphere filled with toxic gases, and river systems became unstable. Instead of vibrant ecosystems, the land was dominated by barren landscapes filled with fungi and bacteria, feeding on decaying matter. One of the great questions of modern paleontology is, why was the recovery so slow? Unlike other mass extinctions, after which life began to diversify again within a few million years, recovery from the Great Dying took more than 10 million years. During this time, ecosystems remained simplified, fragile, unstable. This suggests that the extinction's effects didn't end with the initial crisis. The planet remained locked in a cycle of prolonged imbalance. The climate stayed hostile, ocean chemistry remained altered, and biodiversity crawled instead of exploding. But over time, life's resilience prevailed. New lineages began to emerge. Hardy plants colonized the continents. Amphibians and reptiles expanded again. Eventually, the first archosaurs, the group that would later include crocodiles, dinosaurs, and birds, began to dominate. Earth slowly rose again, but it was a changed planet. The ecosystems of the Triassic bore no resemblance to the lush systems of the late Permian. It was a new world inhabited by survivors and mutations. The Permian-Triassic extinction also carries modern implications. Many of the causes, global warming, ocean acidification, release of toxic gases, oxygen depletion, ecological imbalance, are happening again, this time driven by human activity. Science sees alarming parallels between the Great Dying and the current global environmental crisis. While we are not yet facing an event of that magnitude, the warning signs are in the air and in the sea. In summary, the Permian-Triassic extinction was an absolute turning point in the planet's history. It marked the end of the ancient Paleozoic biosphere and the beginning of a new era. It proved that life can withstand even the worst cataclysms, but it also made clear that there are limits. Earth survived, but paid an immense price, and all of it happened without any external impact. No asteroids. Only through the inner workings of Earth's own geodynamic machinery. The greatest natural tragedy of all time was born from the planet's own depths. Long before dinosaurs walked the Earth, there was an era of forgotten giants. But they weren't colossal reptiles or furry mammals. They were insects. Dragonflies with wings over 70 centimeters wide, millipedes the size of snakes, cockroaches as long as a human forearm. This era, known as the Carboniferous period, between approximately 359 and 299 million years ago, was a time when arthropods ruled terrestrial ecosystems and swampy forests covered vast portions of the planet, especially in tropical and equatorial regions. But this lush, humid, and profoundly strange world collapsed at the end of the period, taking with it the giant insects and their forests. It was a lesser-known extinction, yet essential for understanding the ecological cycles that shaped life. During the Carboniferous, Earth experienced unique atmospheric conditions. Atmospheric oxygen levels reached about 35% compared to today's 21%. This increase was driven by intense photosynthesis from vast tropical forests composed of lycophytes, giant ferns, and primordial trees that absorbed large amounts of carbon dioxide and released oxygen. This oxygen surplus not only influenced global climate, making it wetter and more stable, but also enabled insects to reach sizes never seen again. Because their respiratory systems rely on oxygen diffusing through the body, higher concentrations in the air allowed for greater body size. These humid forests formed closed, dense and permanently waterlogged ecosystems where mosses, fungi and invertebrate animals coexisted in a relatively stable ecological chain. Underground, decomposing plant matter accumulated without being fully broken down, creating immense reserves of organic carbon that, millions of years later, gave rise to the coal deposits we still use today. This is the origin of the period's name, Carboniferous, the time when Earth stored carbon on a scale never repeated, but by the end of the Carboniferous, this balance broke down. Changes in continental configurations, especially the formation of the supercontinent, Pangaea, deeply altered the global climate. The merging of massive land masses created arid, dry continental interiors where tropical forests once thrived. The rise of mountain ranges like the Appalachians redirected moist winds and formed natural barriers to humidity flow. The result? Tropical forests began disappearing on a large scale, fragmenting into isolated pockets before collapsing entirely. This process, known as the collapse of the Carboniferous rainforest, had direct consequences on giant arthropods. With the drop in atmospheric oxygen falling quickly to levels closer to today's, the giant insects lost their biological advantage. Many species couldn't adapt to the new environmental conditions and disappeared. Fossil records show a sharp decline in insect size and diversity right after this transition. The reign of the winged giants had come to an end. The forest loss also impacted terrestrial vertebrates, especially early tetrapods that had evolved in wet, vegetation-rich environments. As drier and more unstable habitats emerged, moisture-adapted groups were replaced by animals with eggs resistant to desiccation, such as the first amniote reptiles. This ecological shift paved the way for the eventual dominance of reptiles in the Mesozoic. Once again, extinction was not just a loss, but a profound evolutionary turning point. Though not classified among the 5 major mass extinctions, the transition from the Carboniferous to the Permian was a significant ecological crisis, particularly for how it reshaped atmospheric composition and terrestrial ecosystems. Marine biodiversity remained relatively stable, but the land underwent a total restructuring. The green, humid world of the Carboniferous gave way to drier plains, deserts, and more resilient vegetation. The planet changed its skin, and life had to adapt again. This episode teaches us something essential. Changes in climate, landscape, and atmosphere can completely redefine the physical and biological limits of life. A small disruption in the carbon cycle or moisture distribution can trigger the silent extinction of entire groups. The giant insects of the past remind us that even the dominant, the adapted, and the prosperous can disappear when the world changes too quickly. And perhaps symbolically, the most tangible legacy of the Carboniferous is not found in fossils, but in the fossil fuels we extract from Earth: coal, oil, gas. Energy that powers our modern society, but also carries the paradox of collapse. By burning this ancestral organic legacy, we are once again heating the planet and altering the carbon cycle, perhaps steering toward a new extinction, this time caused by us. When the planet emerged from the chaos left by the Great Dying at the end of the Permian, almost everything had been wiped out. The oceans were stagnant, the skies thick with volcanic particles and toxic gases, and the continents were covered in arid, desolate landscapes. For a time, Earth was nearly a planetary desert. Biodiversity had been reduced to a critical threshold. Fossils from the early part of the next period, the Triassic, reveal simplified, fragile ecosystems composed almost exclusively of opportunistic and resilient survivor species. And yet, against all odds, life, did not vanish. It endured, reorganized, and slowly began a new evolutionary chapter. This segment is dedicated to understanding how, after the greatest biological cataclysm in Earth's history, life managed to restart from almost nothing. During the first few million years of the Triassic, Earth was a silent world. Tropical forests had disappeared, coral reefs had vanished entirely. The seafloor, once rich in diversity, had become a habitat dominated by bacteria and organisms capable of surviving in low-oxygen environments. It was a world of survivors, and survival often came not from strength or complexity, but from simplicity. Microorganisms adapted to oxygen-poor waters, small reptiles resilient to heat, and drought-tolerant plants were the first to recolonize a deeply wounded planet. Fossil evidence shows that ecological recovery was symmetrically slow. While some life forms expanded within the first 2 or 3 million years, others took more than 8 to 10 million years to return to pre-extinction levels. Coral reefs, complex and highly sensitive ecological structures, took around 14 million years to begin rebuilding. This sluggish pace reveals that, even after the end of the Siberian Traps volcanic crisis, the planet remained chemically unstable for a long time, with oceans too warm, fluctuating oxygen levels, and lingering acid rain. Even so, life's resilience made itself known. Animal groups that had been secondary players during the Permian began to flourish. One of the first to expand was the group of archosaurs, which would later include dinosaurs, pterosaurs, and crocodilians. They displayed remarkable adaptability to arid and unstable environments, quickly dominating large portions of the land. Meanwhile, the remaining synapsids, ancestors of mammals, survived mainly in nocturnal and underground niches, staying hidden and sheltered from the extreme heat. In the oceans, new lineages of mollusks, cephalopods, and bony fish began to diversify slowly. The marine food web, once collapsed, was reconstructed with smaller organisms, more resistant to warm, low-oxygen waters. It was within this context that the first representatives of many modern groups appeared. The world had changed, and the survivors, now the protagonists, would become the architects of the next great biological age. Vegetation also played a fundamental role. The beginning of the Triassic was dominated by ferns, cycads, and primitive conifers, plants well suited to heat and drought. Over millions of years, they gradually rebuilt terrestrial ecosystems, stabilizing soils and reactivating carbon and water cycles. The return of vegetation was essential to reduce atmospheric carbon dioxide, which remained at extremely high levels, and to support herbivorous food chains. Without plants, the restoration of terrestrial life would not have been possible. But why was this rebirth possible? The answer lies in the essence of life itself: adaptation. Even under extreme conditions, some organisms retain the ability to adjust, resist, and alter their behavior or metabolism. The surviving genetic diversity, however limited, still carried the potential to rebuild the world. With each generation, random mutations opened new doors. And slowly, natural selection did its work. Life didn't return to what it was, it transformed. The post-Permian recovery also teaches us that a mass extinction is not the end of life, but the end of a phase of it. Dominant groups fall, and the dominated emerge. Empty niches become invitations for evolutionary innovation. It is within this space of absence and silence that natural selection's creativity flourishes. The rise of the dinosaurs, one of the most iconic chapters in Earth's history, was only possible because their predecessors had been cleared away by the Great Dying. Today, looking at this period is like watching a miracle in slow motion. The world was nearly annihilated, but it was not defeated. Earth kept spinning, the seas calmed, the skies cleared, and life began again. A silent testimony that even the most total collapses, can give rise to new forms of beauty, balance, and diversity. The planet rose from the ashes and continued writing its long, fragile, and extraordinary story. Around 201 million years ago, as the world began to recover from the deep trauma left by the great dying of the Permian, life was already restructuring itself with new forms, new lineages, and new ecological systems. The Triassic period witnessed the emergence of many modern groups of animals and plants in a world still marked by arid climates, fragile soils, and warm oceans. Yet even in this moment of reconstruction, a new mass extinction loomed, and it would become responsible for opening the path to one of the most iconic chapters in Earth's history, the age of the dinosaurs. The so-called Triassic-Jurassic extinction event eliminated a significant portion of terrestrial and marine biodiversity, clearing ecological space for dinosaurs to dominate the planet for more than 135 million years. The Triassic-Jurassic extinction is one of the P5 Great Mass Extinction recognized by scientists. It is estimated that around 50% of all land and marine species disappeared during this event. Entire groups of large amphibians, archaic reptiles, and some synapside lineages were wiped out. In the oceans, ammonoids, bivalves, and rugose corals suffered severe losses. Terrestrial biodiversity was especially affected, with the disappearance of many competing groups of archosaurs, including lineages that might have rivaled the early dinosaurs. But what caused this new collapse, so soon after the planet had begun to rebuild? Once again, the leading suspect is a large-scale volcanism. During this period, the reopening of the Atlantic Ocean and the breakup of the supercontinent Pangaea triggered massive eruptions across the region known today as the Central Atlantic Magmatic Province, CAMP, one of the largest volcanic formations in geological history. Millions of cubic kilometers of basaltic lava were poured over the central belt of what are now the Americas, Europe, and Africa. As with the Siberian traps, these eruptions were accompanied by massive emissions of carbon dioxide and sulfur dioxide, quickly and drastically altering the global climate. The result was a sudden global warming, ocean acidification, disrupted rainfall patterns, and severe climate instability. Ecosystems that had already been fragile since the Permian could not withstand this new shock. The Triassic-Jurassic extinction was not as intense as the previous one, but it was decisive canvas in reorganizing the living world. By eliminating rival predators and herbivores, it opened ecological niches that allowed early dinosaurs, until then small and unimposing, to diversify and occupy all the newly vacated roles. Fossil records show that, immediately following the extinction, dinosaurs began expanding rapidly in size, shape, and behavior. Groups such as sauropods, theropods, and ornithischians emerged in the early Jurassic, marking the beginning of a reign that would last until the end of the Cretaceous. Without the Triassic-Jurassic extinction, dinosaurs might never have become dominant, and another branch of archosaurs, or even synapsids, could have followed a very different evolutionary path. Another important impact of this event was the reorganization of vegetation. With the breakup of Pangaea and changing moisture patterns, gymnosperm plants such as cycads, ginkgos, and conifers came to dominate vast areas, providing food and shelter for the emerging herbivores. The combination of a newly fractured world, new climates, and a cast of versatile survivors allowed the Jurassic to flourish as a new ecological age, with more complex food webs, vast forests, and a rising megafauna. The Triassic-Jurassic extinction also reminds us that the most evolutionarily significant extinctions are not always the largest. Sometimes a moderate collapse, strategically timed, can completely reshape the future of life. By removing the right rivals at the right moment, natural selection creates a vacuum, one that will be quickly and creatively filled by nature. Thus, the Triassic extinction did not merely eliminate forms of life, it paved the way for the biological spectacle of the dinosaurs. It was as if the stage had been cleared, the spotlights repositioned, and the protagonists released to enter. The world was becoming for the first time the world of giant reptiles, winged creatures, long necks, and sharp claws. And all of it thanks to yet another cycle of destruction and rebirth. The planet fell. Again and again, it rose. Throughout Earth's history, the continents have not always been where we see them today. They have drifted, collided, broken apart, and reassembled in a geological cycle that spans hundreds of millions of years. This slow but constant movement, known as the supercontinent cycle, shapes not only the geography of the planet, but also the global climate, atmospheric oxygen levels, and ultimately, life itself. The formation and breakup of supercontinents, such as Rodinia, Pangaea, and Gondwana, are deeply linked to mass extinctions, major atmospheric changes, and biological catastrophes on a planetary scale. Earth has formed several supercontinents throughout its existence. These geological giants are the result of tectonic collisions that unite all land masses into a single continental block. This union has profound impacts on global climate. When continents cluster together, their interiors become dry, arid, and thermally extreme, being far removed from the ocean's moderating influence. Vegetation suffers, evaporation declines, and hydrological cycles shift. This creates vast inland regions that are inhospitable, where many species struggle to survive. Furthermore, the formation of supercontinents directly affects global ocean circulation. When the plates are joined, the number of shallow seas, areas rich in biodiversity, drops considerably. Ocean currents, which depend on the shape and position of the continents, become restricted, leading to the stagnation of large water volumes and a corresponding decline in dissolved oxygen. This oceanic anoxia has been one of the key drivers of marine extinctions throughout Earth's history. During the time of the supercontinent, Pangaea, for instance, a combination of volcanism, extreme climate, and disrupted oceanic flow led to cascading imbalances that culminated in the Permian Triassic extinction event. It wasn't just fire that killed, it was also planetary reorganization. At that time, the planet had become a low-diversity system with intense competition, homogeneous environments, and weakened ecological resilience. When collapse came, it struck with full force. Another crucial element in this process is the atmospheric oxygen level. The interaction between supercontinents, vegetation, and geochemical cycles can raise or lower oxygen concentrations over millions of years. During the Carboniferous period, for example, the formation of vast tropical forests in humid environments drastically increased oxygen levels, allowing insects to grow to gigantic sizes. However, with the collapse of those forests and the continental reconfiguration leading into the Permian, oxygen levels dropped sharply, taking many of those organisms with it. It's also important to note that continental movement influences large-scale volcanic activity. When plates collide or break apart, massive magmatic provinces can form. The Siberian Traps and the Central Atlantic Magmatic Province, CAMP, are examples of volcanic regions directly tied to tectonic shifts. These prolonged eruptions release millions of tons of gases into the atmosphere, disrupting the climate for thousands of years. This context shows how deep geology, surface climate, and biological disasters are intricately connected. On the other hand, the breakup of supercontinents also brings consequences. When Pangaea began to fragment in the early Jurassic, new ocean basins opened, increasing the number of shallow seas and promoting a burst in marine biodiversity. The separation of land masses created new coastlines, new microclimates, new geographic barriers, and with them, new evolutionary opportunities. That's why the breakup of supercontinents is often linked to periods of adaptive radiation, when living organisms diversify rapidly to fill newly opened ecological niches. Thus, supercontinents are silent but powerful actors in the story of mass extinctions. They shape the stage on which life unfolds. They change the rules of the game. And when they collapse or unite, they redraw the boundaries of the biosphere. Plate tectonics, often remembered only for earthquakes and mountains, is in truth a controlling force of life and death on a planetary scale. Today, the continents are still on the move. It is estimated that in a few 100 million years, a new supercontinent, perhaps called Amasia, may form. And with it will come new changes in the ocean's climate and oxygen, and perhaps new cycles of life's expansion and collapse. Earth breathes slowly in cycles of destruction and rebirth, and supercontinents are a vital part of that deep, relentless rhythm. It was a morning like any other at the end of the Cretaceous period. The planet pulsed with life. Dinosaurs dominated the forests and plains. Pterosaurs soared through the skies. The oceans teemed with giant marine reptiles, and dense forests stretched across entire continents. But this era of splendor was about to end in an instant. In a single second, an asteroid more than 10 kilometers in diameter struck what is now the Yucatan Peninsula in Mexico. releasing energy greater than 1 billion Hiroshima atomic bombs. The Chicxulub impact was more than a celestial collision. It was a mass extinction event that marked the end of the dinosaur age and the beginning of the modern world. The asteroid traveled at over 70,000 kilometers per hour. When it hit Earth, it carved out a crater more than 180 kilometers wide and nearly 20 kilometers deep. The energy release was so intense that rocks, oceans, and even part of the Earth's crust vaporized. A cloud of incandescent debris was launched into the stratosphere and beyond, spreading throughout the atmosphere. Within hours, Earth was shrouded in global darkness. Sunlight was blocked for months, possibly years. Temperatures plummeted. Photosynthesis ceased. The food chain collapsed. It was the beginning of an impact winter. Evidence of this cataclysmic event is found worldwide. In geological layers across the planet lies a thin band rich in iridium, a rare element in Earth's crust but abundant in asteroids. This layer, visible in fossils and rocks, precisely marks the boundary between the Cretaceous and Paleogene, the famous KPG boundary. Below the layer, fossils of dinosaurs, ammonites, and many marine reptiles. Above it, a transformed world where mammals and birds began to flourish. The impact did not just wipe out the dinosaurs. It caused the extinction of approximately 75% of all species on the planet. All large non-avian reptiles vanished. Countless species of plants, insects, mollusks, and plankton were also eradicated. Oceans witnessed the collapse of entire food webs, and continents became ash-covered wastelands, with global forest fires fueled by dry vegetation and extreme temperatures. Beyond the impact itself, the planet suffered a climatic chain reaction. Sulfur released from the vaporized rock triggered acid rain that devastated forests. Global cooling gave way to extreme thermal oscillations, while the oceans underwent severe acidification. The world fell silent. For the second time in its history, life came close to a total reset. Yet again it endured. Among the few survivors were birds, the only dinosaurs to persist, as well as small mammals, amphibians, crocodilians, turtles, and some lineages of fish and plankton. The ability to hide, hibernate, eat a variety of foods, and live in underground or aquatic environments proved decisive for avoiding extinction. The great predators of the past, tyrannosaurs, spinosaurids, mosasaurs, simply disappeared. The ecological throne was left empty, and it was this vacancy that allowed mammals to rise. With the dominant species gone, the small, furry, nocturnal survivors began to diversify. Within just a few million years, the first primates would appear, along with the ancestors of whales, ungulates, and modern carnivores. The Chicxulub impact didn't just end an era, it began ours. The Chicxulub crater, now buried beneath the plains of the Yucatan Peninsula, is more than a geological mark. It is a brutal reminder of life's fragility, a warning that even in times of apparent stability, the cosmos can intervene unexpectedly and irreversibly. The sky, which for millions of years had been only a backdrop, in that instant became the executioner. Studying the Chicxulub impact helps us understand not only the past, but the potential of future events. Asteroid monitoring is now a real branch of planetary science. After all, if history has taught us anything, it is that life on Earth is resilient, but not invulnerable, and the universe beyond, silent and indifferent, remains filled with rocky fragments drifting through the dark. On the scale of geological time, most events unfold slowly over millions of years. But some moments last only seconds, and yet they change the history of the planet forever. The day the Chicxulub asteroid collided with Earth was one of those pivotal instants. A microscopic point in the timeline of the universe, but one that closed an entire era of life. This chapter is not about the mass extinction itself, but about the day of the impact. What happened in the hours and days immediately after the sky fell? What was the last day of the dinosaurs like? Imagine the planet in its full splendor, at the end of the Cretaceous. Dense forests covered vast regions, warm oceans teemed with life. Pterosaurs flew through clear skies. Dinosaurs of all shapes and sizes grazed, hunted, and cared for their young. It was a vibrant world, full of color, sound, and interaction. Then suddenly a bright point appeared in the northern sky. Small at first. Within minutes, it became a moving star, growing in brightness and speed. The Chicxulub asteroid was entering Earth's atmosphere at more than 20 times the speed of a bullet. The moment of impact released energy equivalent to over 100 trillion tons of TNT. The collision instantly vaporized the Earth's crust, the asteroid, and everything nearby. A sea of fire spread. The ground shook with seismic waves that traveled across the globe. Tsunamis hundreds of meters high swept over coastlines, and perhaps most devastating of all, billions of tons of dust, sulfur aerosols, and molten rock fragments were ejected into the atmosphere, wrapping the planet in a thick, dark, scorching shroud. Within the first few hours, darkness fell like a global eclipse. Sunlight vanished. Temperatures dropped. Small molten glass spheres, called tektites, rained from the skies, formed by the intense heat of the impact. These fragments fell like burning hail, igniting forests and vegetation across the globe. Worldwide wildfires erupted, consuming atmospheric oxygen and releasing even more carbon. Earth had become a furnace, followed by a deep freeze. Within just a few days, photosynthesis stopped. Without sunlight, plants ceased to produce energy. Without plants, herbivores perished. And without herbivores, the great carnivores soon followed. It was a total collapse of the food chain. Extinction didn't come just from the impact, but from the ecological crisis it unleashed. Food scarcity and rapidly shifting climates made the planet uninhabitable within weeks. But what about the dinosaurs? What do we know about their last-day casa? Fossils found in sites like Hell Creek in the United States suggest that many dinosaurs did not die instantly, but over the hours and days that followed. Some specimens, including Triceratops and hadrosaurs, were preserved with astonishing detail, buried under layers of tektites and volcanic ash, as if they had been entombed in the very moment of disaster. A site in North Dakota even suggests that fish died choking on molten glass particles falling from the sky, demonstrating the speed and violence of the cataclysm. The impact may have also generated sound waves so powerful they circled the planet, as well as debris ejected into Earth's orbit. Some of that material re-entered the atmosphere, heating the skies to such extremes that it caused a global broiler, roasting surface-dwelling creatures that couldn't find shelter. In this apocalyptic scenario, only small underground aquatic or highly mobile creatures had a chance to survive. That day, known scientifically as the K-Pig boundary, marks the end of the Mesozoic and the beginning of the Cenozoic. Life would never be the same again. And while it may seem like a purely apocalyptic event, and it certainly was, it was also the beginning of something new. Without that impact, dinosaurs might still rule the Earth today. And we perhaps wouldn't be here. The sky fell, the era ended, and a new world rose from the dust. Today, the Chicxulub crater lies hidden beneath layers of sediment and tropical forest, silent, but its scar still pulses in the geological memory of the planet. A reminder that the course of life can change in an instant, and that even the grandest dominance can be ended by a wandering fragment from space. After the apocalyptic collision that marked the end of the Cretaceous, the planet plunged into deep darkness. But the true biological collapse that followed the Chicxulub impact wasn't caused solely by the initial explosion, earthquakes, or colossal tsunamis. What killed most life in the months and years that followed was a devastating and silent phenomenon, the so-called impact winter, a period of extreme global cooling triggered by dust, ash, sulfur aerosols, and soot, launched into the upper atmosphere, a thick veil that blocked sunlight and completely disrupted Earth's natural cycles. Within hours of the impact, the planet was already shrouded in darkness. The ejected debris rose so high into the atmosphere that it reached the stratosphere, where it cannot be easily washed away by rain. These particles remained suspended for months or even years, reflecting solar radiation back into space. The result was an abrupt global temperature decline, especially in the tropical and temperate zones that sustained much of the planet's biodiversity. This severe cooling had multiple consequences. First, photosynthesis stopped. Without light, plants couldn't produce energy, and the foundation of the entire food chain collapsed. Phytoplankton in the oceans, responsible for much of Earth's oxygen production and the base of marine food webs, were also drastically affected. Herbivores, deprived of food, died en masse. Carnivores soon followed. The cycle was brutal and swift. Temperatures dropped unevenly, with estimated declines of between 10 and 20 degrees Celsius, depending on the region. In subtropical and temperate climates, unseasonal frosts appeared, rainfall patterns were disrupted, and rapid desertification set in. Coastal environments, once home to thriving marine ecosystems, became dead zones. In many regions, ocean acidification caused by acid rain worsened the crisis, dissolving calcium carbonate essential for organisms like corals, mollusks, and shelled plankton. The impact winter was not just a fleeting cold snap. It lasted long enough to redefine entire ecosystems. It's estimated that the direct cooling effects persisted for at least 3 to 5 years, with some climatic consequences lasting up to a decade. That means 10 years of scarcity, ecological instability, and collapse of large organisms. For dinosaurs, dependent on vast territories, high food intake, and environmental stability, it was the final blow. Even those that survived the initial impact could not endure the world that followed. But while the giants perished, the small survived. Burrowing mammals, birds capable of long-distance flight, aquatic reptiles, resilient insects, and certain fish species adapted to low-oxygen environments managed to endure the impact winter. The key to survival was adaptability. Animals that could hibernate, store food, consume varied diets, or tolerate cold conditions had the highest chances of making it through. Another important factor was the resilience of Earth's geochemical cycles. Over the years, atmospheric particles began to dissipate. Residual carbon dioxide from wildfires and the impact gradually warmed the planet. As sunlight returned and the climate stabilized, Earth entered a new warming phase, the post-impact thermal rebound. In this new environment, with empty ecosystems and few competitors, survivors had fertile ground to expand and diversify. The impact winter also helps us understand just how interconnected Earth's natural systems are. A sudden atmospheric change affected light, climate, soil, oceans, vegetation, and food chains, all within weeks. It's a stark reminder that biosphere stability depends on the delicate balance of highly sensitive variables. Today, scientists use the impact winter as a model to study similar events that could occur in the future, whether through another asteroid collision, massive volcanic eruptions, or even nuclear war. The concept of nuclear winter, for example, stems directly from Chicxulub-related research. Earth has endured this before, and could again if we fail to learn from its scars. What remained after that winter was not just devastation. It was called the rebirth of life on new terms. From the cold darkness and silence emerged the ancestors of modern mammals, birds, primates, and eventually ourselves. The Earth's longest night gave way to a new evolutionary dawn. When we talk about mass extinctions, it's common to think only of the 5 major biological catastrophes that reshaped life on Earth: the Ordovician, Devonian, Permian, Triassic, and Cretaceous events. However, between these major collapses lie silent, obscure, and equally dangerous episodes that didn't reach the same level of global destruction, but at times nearly wiped out biodiversity in specific regions or within particular groups. These are known as minor extinctions, or localized biological crises, which leave deep marks in the fossil record, even if subtle at first glance. These silent extinctions are no less important. They act as rehearsals for collapse, sudden pauses in evolutionary growth, or interruptions in promising lineages. Often their severity is only recognized by analyzing the absence of certain groups in subsequent geological layers, or by a sudden halt in fossil diversity. One of the most studied examples is the Cenomanian-Turonian oceanic anoxic event, which occurred around 94 million years ago during the Cretaceous. At that time, the oceans suffered a sudden oxygen collapse, resulting in the extinction of numerous marine groups, particularly plankton, mollusks, and pelagic organisms. Another significant and nearly unknown outside scientific circles event is the TJ event, Tuacian Early Jurassic, which happened approximately 183 million years ago. It coincided with an episode of intense volcanism in the South Atlantic magmatic province, which released large amounts of carbon dioxide into the atmosphere. Ocean acidification, global warming, and the resulting anoxia caused a sharp decline in marine diversity. It was a considerable loss of species, mainly ammonites, brachiopods, and marine reptiles, though without the complete collapse of food chains, hence its classification as a minor extinction. Another relevant example is the extinction event at the end of the Eocene about 34 million years ago. During this period, global climate shifts led to the cooling of the Earth and the formation of the Antarctic ice sheet. This cooling, associated with a possible drop in atmospheric carbon dioxide, caused a sharp decline in tropical species and forced the migration or extinction of many groups of mammals, birds, and plants. Once again, it wasn't a total collapse, but a forced ecological reshuffling. Silent extinctions also impact specific groups. Trilobites, for instance, experienced several gradual declines in diversity throughout the Paleozoic before vanishing completely at the end of the Permian. Another interesting case is the graptolites, common fossils in Ordovician and Silurian rocks, which slowly and almost imperceptibly disappeared due to constant environmental changes. These slow-motion losses are also part of the mosaic of ecological crises. Moreover, some of these quiet events happened abruptly, but were limited to specific regions of the planet. Local climate changes, isolated volcanic resurfacings, basalt floods in restricted provinces, or even changes in marine chemistry limited to interior seas caused regional ecological collapses, invisible on a global scale, but fatal to the life forms inhabiting those areas. Marine life in European seas, for example, was severely affected during some of these episodes, while other regions of the world remained relatively stable. Modern science acknowledges that these minor events are cumulative. They create evolutionary bottlenecks, where entire lineages are shortened or eliminated, forcing new evolutionary paths. And sometimes it's the survivors of these episodes who later become the dominant life forms of future eras. Thus, even extinctions that don't wipe out 75% of species leave lasting scars. Today, these silent extinctions serve as unsettling parallels to the current biodiversity crisis. The so-called sixth mass extinction, which many scientists believe is already underway, doesn't have a single event or sudden cause. It unfolds slowly, day by day, with the loss of plant species, insect collapse, disappearance of coral reefs, and habitat degradation. There is no visible crater or erupting volcano, but the effects are real and potentially devastating. These quiet collapses from the past show that it doesn't take an asteroid to decimate life. Sometimes all it takes is a steady sequence of subtle and continuous pressures, and the world begins to disappear in silence. For millions of years, Earth was home to colossal creatures that roamed cold, vast, and untamed landscapes. Woolly mammoths, saber-toothed cats, giant ground sloths, armored glyptodonts, primitive bison, cave bears, all formed what we call the megafauna of the Pleistocene, the Ice Age. These extraordinary animals, adapted to extreme environments, dominated boreal forests, icy tundras and frozen steppes for over 2 million years, yet in a relatively short window, between 50,000 and 10,000 years ago, most of them vanished. This wave of extinctions, although not among the Big Five, was a profound global and transformative event, and perhaps the one most directly linked to human presence. The Pleistocene, which began around 2.6 million years ago, was marked by repeated cycles of glaciations, with intense cold periods alternating with milder intervals known as interglacials. During the Ice Ages, massive ice sheets covered vast regions of North America, Europe, and Asia, and sea levels dropped by more than 100 meters, connecting continents through natural land bridges. The fauna of the time adapted to the cold: thick fur, large bodies for heat retention, and specialized diets based on frozen and sparse vegetation. However, around 12,000 years ago, at the end of the last glaciation, known as the Worm or Wisconsin glaciation, the planet's climate began to warm rapidly. The glaciers retreated, sea levels rose, and ecosystems were drastically altered. Landscapes once dominated by tundra and cold steppes were replaced by dense forests and warmer climates. This transformation reduced food availability for many megafaunal species that depended on vast open areas and seasonal vegetation to survive. That climate shift alone would have been challenging. But there was another crucial factor: humans. As Homo sapiens spread across the planet, hunting, altering landscapes, and competing for resources, the pressure on large animals increased significantly. Fossil and archaeological evidence shows that in nearly every continent, the arrival of humans coincides with a sudden decline in local megafauna. In North America, for example, Over 70% of large mammal species disappeared within a few thousand years after humans crossed the Bering Land Bridge. The same pattern repeated in Australia, where the first Aboriginal peoples arrived about 50,000 years ago. Soon after, giant marsupials like the Diprotodon, the size of a hippo, giant kangaroos and predatory reptiles like Megalania vanished. In New Zealand, where humans arrived only around 1,000 years ago, the native megafauna also disappeared quickly, including the moa birds and their natural predators. A similar story unfolded in Madagascar. This correlation between human presence and megafaunal extinction gave rise to the overkill hypothesis. According to this theory, humans, even in small populations, hunted efficiently and persistently, destabilizing populations that had no natural defenses against intelligent social predators. Hunting, combined with climate change and habitat fragmentation, created an unsustainable scenario for large animals. But why the large ones? The answer lies in biology. Larger animals require more resources, have lower reproductive rates, take longer to reach sexual maturity, and are less agile in adapting to rapid pressures. This makes them more vulnerable to environmental imbalances and targeted hunting. While small mammals, birds, and reptiles survived, the giants could not keep up with the pace of change. The extinction of the megafauna had lasting consequences. It deeply altered ecosystems, nutrient cycles, and even vegetation. Without large herbivores, forests expanded into areas once dominated by grasslands, changing natural fire regimes and soil composition. The disappearance of large seed dispersers also affected many plants that still bear fruits adapted to animals that no longer exist, the so-called orphan fruits. Today, the only large-scale surviving megafauna is concentrated in Africa, and to a lesser extent South Asia, regions where coevolution with humans allowed large animals to develop defense behaviors, migration strategies, and reproductive adaptations to coexist with hunters. In other words, where humans and giants evolved together, extinction was less severe. This chapter teaches us that human activity, even in its most primitive stages, already had global impacts. It also shows how climate and ecological pressure don't need to be catastrophic on a planetary scale to cause profound transformations. Sometimes, just a few decades of continuous change can completely rewrite the course of life. And perhaps most importantly, the extinction of the Pleistocene megafauna is not as distant as it seems. It's recent, well documented, and serves as a direct mirror for the pressures we now place on elephants, rhinos, polar bears, whales, and so many other living giants. The Ice Age may be over, but the challenge of preserving the planet's colossi continues. Throughout Earth's history, mass extinctions have been triggered by overwhelming natural forces, continent-wide volcanism, abrupt climate shifts, asteroid impacts, the formation of supercontinents, or extreme glacial cooling. But now, in the present day, a new agent is driving the collapse: us. Since the beginning of the Industrial Revolution, and with increasing intensity in recent decades, humanity has transformed the planet at a speed no other species in the history of the biosphere has ever achieved. And scientists are increasingly convinced that we are experiencing a new mass extinction, the sixth great extinction, silent, fragmented, and global. Unlike previous events, marked by a single catastrophic trigger, the sixth extinction is a diffuse, multifactorial phenomenon. It is not initiated by a celestial impact or a mega eruption, but by a combination of human actions that together are profoundly destabilizing Earth's ecological balance. Deforestation, pollution, hunting, introduction of invasive species, habitat fragmentation, ocean acidification, global warming, and uncontrolled urban growth all create a toxic ecosystem where thousands of species simply cannot survive. According to estimates from the International Union for Conservation of Nature, IUCN, over 1 million species are currently at risk of extinction, and the rate of loss is alarming. We are wiping out species thousands of times faster than the natural background rate, the rate expected over geological time. Most disturbing is that many of these losses go entirely unrecorded. Insects, fungi, microorganisms, endemic plants. Many disappear before they are even described by science. It is an invisible extinction, happening day by day, forest by forest, reef by reef, lake by lake. This silent disappearance has consequences far beyond biology. Species loss disrupts ecological networks, affects pollination, destabilizes soil, reduces fertility, alters rainfall patterns, and encourages the spread of pests and disease. When an ecosystem collapses, the environmental services it provided, often without our awareness, cease to exist. And that directly impacts the economy, food security, public health, and even geopolitical stability. One of the most symbolic signs of this ongoing collapse is the decline of pollinating insects such as bees, moths, and butterflies. Across various regions of the world, entire populations are disappearing due to pesticides, climate change, and habitat loss. Without them, agricultural food production is at risk, and the balance between plants and animals begins to unravel in cascading effects. This is only one example among many. In addition, the oceans are slowly dying. Acidification caused by atmospheric carbon dioxide absorption, combined with rising temperatures and pollution from plastics and heavy metals, is driving coral reefs, the cradle of 1/4 of all marine life, into global collapse. Phenomena like coral bleaching have become common. As we lose the reefs, we also lose the species that depend on them, and the human communities that rely on fishing and tourism tied to these habitats. It's important to understand that this time, there will be no iridium layer or colossal crater to mark the event. The sixth extinction leaves no sudden, spectacular signs. It accumulates in statistics, reports, forests vanishing from satellite images, dead zones spreading across ocean maps, bird songs falling silent, and for that very reason, it is harder to stop, because we don't feel it as a tragedy, but as normality. The debate over whether we are already in a mass extinction still divides parts of the scientific community. Some experts argue that the total number of species lost has not yet reached the 75% threshold that defines a true mass extinction, but most agree that if the current rate continues over the coming decades or centuries, we will reach that mark. And unlike previous extinctions, this one is reversible, because the driver is us, and therefore the solution is also in our hands. Climate mitigation, habitat restoration, pollution control, banning of lethal pesticides, protection of endangered species, reduced meat consumption, promotion of regenerative agriculture, ecological education. The tools exist. The challenge is implementing them on a global scale, and with enough urgency to halt the collapse before it becomes irreversible. The sixth extinction is still ongoing, and perhaps for the first time in Earth's history, an extinction could be stopped by the very species that caused it. But time is running out, and with each passing year, another lineage vanishes forever. Lineages that carry millions of years of evolution, that survived volcanoes, ice ages, and asteroids, but will not survive modern civilization unless it changes. Over millions of years, Earth has endured impersonal and overwhelming forces: supervolcanoes, climate shifts, continental drift, celestial impacts, glacial cycles. Yet none of these events had awareness. None made decisions, devised plans, or crafted tools. That changed radically with the emergence of Homo sapiens. For the first time in the planet's history, mass destruction is not merely the outcome of natural forces. It is driven by a self-aware species, capable of foresight, planning, and still, destruction. Modern humans emerged around 300,000 years ago, but their most profound impact on the biosphere began only in the last tens of thousands, and it was exponential. With each new technological leap, humanity's ability to reshape the environment expanded disproportionately. From mastering fire to inventing agriculture, from urbanization to industrialization, we progressively turned nature into resource, biodiversity into commodity, and ecological balance into unchecked consumption, not as an exception, but as a civilizational norm. Today, the primary direct causes of the ongoing mass destruction are anthropogenic. Deforestation, particularly in tropical rainforests, is responsible for the loss of millions of hectares of habitat every year. Large-scale agriculture, with monocultures and intensive use of agrochemicals, wipes out entire ecosystems. Industrial pollution contaminates rivers, oceans, soils, and food chains. Unrestrained greenhouse gas emissions rapidly alter the global climate, overheating the planet and melting polar ice caps. Uncontrolled urbanization transforms entire landscapes into grids of concrete and asphalt. Infrastructure such as dams, roads, and mining operations fragment habitats and isolate animal populations, leading many to genetic extinction. Invasive species, introduced by humans, whether deliberately or not, destabilize ecosystems and replace native species around the world. And then there is hunting, overfishing, animal trafficking, and overexploitation of natural resources. All of this unfolds in a deeply interconnected manner. A classic example is the Amazon. As forests are cleared for cattle and soy, the region's water balance is disrupted. This reduces rainfall in distant areas, harms agriculture, increases fire risk, releases stored carbon, and pushes species to the brink of extinction. The loss of a single tree doesn't just affect a patch of land, it affects the planet. But the human impact is not only physical or biological, it is also cultural and symbolic. The way we perceive nature shapes our collective decisions. For centuries, the belief that Earth exists to be dominated has influenced policies, religions, and economies. The notion that humans are above nature, rather than part of it, has created a chasm between progress and sustainability. Even in the face of constant scientific warnings, destruction continues. There is, however, a critical point. Never before has a species possessed so much power to reverse its own impact as humans do. We have knowledge, science, technology, historical memory, and the capacity for collective action. But we also have limited time. The so-called mitigation window, the period during which we can still prevent total collapse, is closing rapidly. And as we debate, each day sees the extinction of species that took millions of years to evolve. The role of humanity is therefore ambiguous. We are the drivers of collapse, but also the only ones capable of stopping it knowingly. This demands a profound change in how we relate to the world. It's not enough to conserve isolated areas or pass laws that go unenforced. We must rebuild a culture of coexistence with the planet, where development is no longer synonymous with destruction, and where progress walks hand in hand with preservation. The fossil record of the future will say much about us. Perhaps a thin layer rich in plastics, heavy metals, radionuclides, and artificially cultivated species will be all that remains. A new iridium layer, this time human-made. The only question that remains is, what kind of mark do we want to leave behind? The Holocene epoch, which began approximately 11,700 years ago, is an extraordinary exception in Earth's long history. It represents an unprecedented period of climatic stability, characterized by moderate temperatures, regular seasonal patterns, and widespread ecological balance. This relative calm allowed humanity to develop agriculture, animal domestication, the first cities, empires, and eventually global civilization. Yet this same era that enabled us to flourish as a species also marks the beginning of a rapid and continuous process of biodiversity loss, which now threatens the very foundation of life. During the Pleistocene, global biodiversity was shaped by glacial and interglacial cycles. Many species could migrate or adapt to the changing conditions, but the Holocene brought a more stable climate, which allowed the rise of as complex and specialized ecosystems such as tropical rainforests, coral reefs, and temperate grasslands. These environments came to host millions of species of plants, fungi, animals, and microorganisms in delicate and interdependent arrangements. However, it was within this very context of stability that humans began to intervene massively. The first major biodiversity losses during the Holocene coincided with the spread of agriculture. As forests were cleared to make way for crops, hundreds of endemic species silently vanished. Fires, irrigation systems, and domesticated animals completely altered the dynamics of soils, rivers, and local climates. Even so, for thousands of years, these impacts remained relatively regional and contained. It was in the 18th century, with the Industrial Revolution, that acceleration began irreversibly. The burning of coal and later oil increased carbon dioxide emissions, initiating modern global warming. Urbanization grew exponentially, creating corridors of concrete and fragmenting habitats. The demand for raw materials led to the predatory exploitation of forests, mountains, rivers, and oceans. And global trade, driven by ships and later airplanes, spread invasive species, diseases, and pollutants to every corner of the planet. Today, we live in what many scientists already refer to as the Anthropocene, a proposed new geological epoch within or following the Holocene, defined by the impact of human activity on the Earth system. This impact is so deep that measurable changes in the carbon, nitrogen, and phosphorus cycles, in the atmosphere's composition, in the oceans, and even in sediment and fossil records, are already evident. In other words, our presence has altered the planet in a measurable and lasting way, and biodiversity is among the most severely affected. The current extinction rate is estimated to be 100 to 1,000 times higher than the natural background rate. Most alarmingly, a large part of this loss is happening in tropical environments, the planet's richest and most vulnerable ecosystems. The Amazon, the Congo Basin, Borneo, Madagascar, the Galapagos Archipelago, the Pacific and Caribbean coral reefs, all of these biodiversity hotspots are at risk of ecological collapse. Additionally, the Holocene saw the rise and expansion of suck industrial fishing, responsible for the depletion of global fish stocks. Whales, sharks, reef fish, and deep-sea species were harvested on unimaginable scales, using techniques that not only target species, but destroy entire marine ecosystems. The destruction of mangroves, bottom trawling, and chemical pollution have turned vast coastal areas into submerged deserts. Another major driver of biodiversity loss is the intensive use of pesticides and fertilizers. The modern agro-industrial model, based on monocultures, drastically reduces genetic and ecological diversity. Bees and other pollinators are disappearing on a global scale. Soils are becoming biologically depleted. Groundwater carries toxic residues, and species adapted to balanced ecosystems simply cannot survive in artificial landscapes. It is important to remember that biodiversity loss is not just a tragedy for animals and plants. It directly affects human health, food security, climate stability, and the global economy. Rich ecosystems are more resilient to climate change, protect against natural disasters, filter water, stabilize soil, and provide medicines, food, and materials. When biodiversity collapses, the entire web of life weakens, including our own. The Holocene, which began as a climatic blessing, is now being corroded from within. If we do not change our patterns of land use, consumption, energy, and production, the stability that sustains us could become nothing more than a geological memory. We still have time, but the clock is ticking. Deforestation is, without a doubt, one of the main drivers of ecological destruction in our time. It's not merely about cutting down trees, it's about removing the living foundation of entire ecosystems, breaking food chains, altering microclimates, interrupting hydrological cycles, and releasing carbon stored for centuries into the atmosphere. It is more the mutilation of the biosphere in real time, and its impact is so profound that it can be compared in functional scale to the geological triggers of past mass extinctions. But this time the cause isn't natural. It's human, ongoing, and intentional. Tropical forests like the Amazon, the Congo Basin, and the forests of Southeast Asia hold the planet's greatest biodiversity. They are living genetic libraries of life. In just 1 hectare of Amazon rainforest, there may be hundreds of tree species, thousands of insect species, and hundreds of birds and mammals. These ecosystems function as moisture pumps, recycling water, forming clouds, and feeding flying rivers that sustain rainfall thousands of kilometers away. When destroyed, the entire climatic system is thrown off balance. Large-scale deforestation, primarily for cattle ranching, soybean farming, mining, and illegal logging, triggers a cascade of effects. First, it releases massive amounts of carbon dioxide into the atmosphere, directly contributing to global warming. Second, it much reduces the planet's capacity to reabsorb that CO2, as fewer trees mean less photosynthesis. Third, it interrupts the water cycle, reducing rainfall and making entire regions drier and more susceptible to wildfires. These fires, in turn, worsen the problem. Often they are started intentionally to clear forested land. However, in a hotter, drier climate, the fires spiral out of control, spreading across vast areas. The carbon released accelerates warming. The heat dries out the soil loses fertility, plants fail to grow back, and in just a few years, once fertile areas become ecological deserts. This is the so-called point of no return. When an ecosystem crosses its resilience threshold and can no longer regenerate on its own, recent studies warn that the Amazon is dangerously close to this threshold. If destruction continues at the current rate, we could witness the savannization of large portions of the rainforest, an irreversible transition from a humid to a dry biome, with colossal biodiversity loss and a radical shift in rainfall patterns across South America. This wouldn't just devastate local fauna and flora, but would compromise agriculture, water supply, energy production, and the social stability of millions of people. This process is not exclusive to the Amazon. The forests of Borneo, Sumatra, Madagascar, and the belt of the Cerrado and Pantanal lace face similar realities. In all cases, deforestation is driven by a mix of economic greed, lack of enforcement, permissive policies, and a global culture of accelerated resource consumption. The forest stops being seen as a living ecosystem and starts being treated as an obstacle to production. Moreover, deforestation contributes to the emergence of new pandemics. By invading wild habitats and bringing human populations closer to wildlife, the risk of zoonoses, diseases transmitted from animals to humans, increases. The COVID-19 virus is just the most recent example of a phenomenon that will likely intensify if we continue breaching the natural barriers between species. There is also a silent impact on culture and knowledge. Indigenous peoples and traditional communities who have lived in harmony with these biomes for millennia are being displaced, criminalized, and forgotten. Along with them, vanishes ancestral knowledge about medicinal plants, sustainable land management, natural astronomy, languages, and myths. A collapse that is not only biological, but also cultural and spiritual. What we are witnessing at its core is a modern ecological collapse, accelerated by short-term economic interests and sustained by global systems of production and consumption. And like in past extinctions, the effects are not isolated. They spread, accumulate, and reinforce each other. Deforestation fuels warming. Warming fuels drought. Drought fuels wildfires. Wildfires fuel ecological collapse. And collapse clears the way for more deforestation. It is a vicious cycle, but it can be broken. It requires urgent, systemic, and collective action. The forest is not just a resource. It is a condition for existence. And without it, there is no balance, no biodiversity, and no future. The ocean covers more than 70% of Earth's surface. It is the cradle of life, the planet's thermal regulator, the largest oxygen producer, the biggest carbon reservoir, and the habitat of most known and unknown life forms. But silently, the oceans are falling ill. And perhaps no other part of the biosphere is undergoing such deep, rapid, and dangerous transformations as marine environments. In this section, we dive into the depths of the crisis threatening the blue heart of the planet, ocean acidification, and the massive loss of marine biodiversity. When we talk about climate change, we often picture the atmosphere, heat, and hurricanes. But it is the ocean that absorbs more than 90% of the excess heat generated by the greenhouse effect, and about 25 to 30% of all carbon dioxide, CO2, emitted by human activity. For a long time, this absorption acted as a planetary buffer. Without it, global warming would have already rendered many regions uninhabitable. However, this protective role comes at a steep biological cost. The chemistry of the ocean is changing, and fast. When CO2 comes into contact with seawater, it reacts with water molecules to form carbonic acid. This acid lowers the water's pH, making the environment more acidic. Since the Industrial Revolution, the average ocean pH has dropped from 8.2 to about 8.1. It may seem small, but this represents about a 30% increase in global ocean acidity, and this acidification has devastating effects on a wide range of marine organisms. Those most affected are the organisms that rely on calcium carbonate to build their structures, such as corals, mollusks, calcareous plankton, and certain crustaceans. As acidity increases, it becomes harder to form strong shells and skeletons. In some cases, already formed structures begin to dissolve. This doesn't just impact individual species, it affects entire food chains. When shelled plankton disappear, the fish that feed on them disappear too, and larger predators follow. One of the most iconic symbols of the current marine crisis is coral reefs. These ecosystems, although covering less than 1% of the ocean floor, host around 25% of all marine species. They are vanishing at an alarming rate due to acidification, rising water temperatures, and pollution. Coral bleaching, when symbiotic algae are expelled, leaving corals colorless, dysfunctional, and eventually dead, now affects more than 50% of Australia's Great Barrier Reef, with similar events reported across all tropical oceans. Another profound impact is the loss of marine oxygen. As ocean temperatures rise, their ability to retain oxygen declines. This gives rise to areas called dead zones, where oxygen levels are so low that nearly no organisms can survive. These zones have always existed naturally in some regions, but human activity, especially runoff from agricultural fertilizers, has greatly expanded them. The dead zone in the Gulf of Mexico, for example, now exceeds 20,000 square kilometers in summer. Industrial fishing worsens the crisis. Species such as tuna, cod, salmon, flounder, sharks, and many others are collapsing in numbers, victims of overfishing, bycatch, and the destruction of habitats like mangroves, estuaries, and seagrass beds. Many of these species don't have time to recover before being caught again. The disappearance of large predators disrupts the ecological balance of the seas, allowing opportunistic species and toxic algae to proliferate. Furthermore, the ocean is literally being suffocated by plastic. Millions of tons of plastic waste enter the seas every year, forming massive floating garbage patches and microplastics, which have been found in the stomachs of birds, whales, fish, and even in table salt. These particles accumulate toxins and enter the food chain, eventually reaching humans. Microplastics are now in the water we drink, the food we eat, and even the air we breathe. All of this leads to a troubling realization. The ocean is not infinite. Its capacity to absorb impacts has limits, and we are dangerously close to exceeding them. The combination of acidification, warming, oxygen loss, pollution, and overfishing is creating a scenario of marine ecological collapse not seen since the end of the Permian. But as with all the crises discussed so far, there is still time. Preserving mangroves, reducing plastic use, protecting marine areas, limiting predatory fishing, controlling land-based pollution, and reducing greenhouse gas emissions are all possible and urgent actions. The ocean is not just a resource or a view, it is a living, dynamic system essential to life, and if it collapses, we collapse with it. Most life on Earth is invisible to the eye. It exists on microscopic scales, in silent biochemical cycles beneath the ground, within ocean currents, on the surfaces of leaves, in the soil's depths, and inside living bodies. It is at this level, invisible but essential, that one of the most profound and overlooked dramas of the current mass extinction is unfolding. The slow death of biodiversity through chemical contamination, diffuse pollution, and systemic poisoning. And at the heart of this global poisoning is a human creation that is omnipresent, durable, and persistent: plastic. Invented in the early 20th century as a versatile and resilient material, plastic revolutionized every industrial sector, from medicine to construction, from technology to food. However, what makes it so useful is also what makes it toxic to the biosphere. It doesn't go away. It fragments, spreads, and accumulates. Since the 1950s, over 9 billion tons of plastic have been produced, and more than 60% of that amount still exists somewhere on the planet. In landfills, forests, rivers, seas, or inside living organisms. Larger plastics, like bottles, bags, and fishing nets, cause obvious problems. They suffocate animals, entangle coral reefs, blanket mangroves, and form floating islands of garbage. But the real collapse is happening on another scale: microplastics and nanoplastics. Over time, sunlight, wind, and water break plastics down into tiny fragments, smaller than grains of rice, and even invisible to the human eye. These fragments have already been found in clouds, glaciers, plankton, breast milk, human placentas, and brain tissue. The contamination is total. Many microplastics act like chemical sponges, absorbing toxic pollutants such as pesticides, heavy metals, and hydrocarbons. When ingested by marine and terrestrial organisms, these materials enter the food chain and accumulate in living tissues, disrupting metabolism, reproduction, and nervous systems. A contaminated plankton may be eaten by a small fish, which is eaten by a larger one, eventually ending up on human plates in an invisible yet very real cycle of self-poisoning. Chemical pollution extends far beyond plastic. Pesticides, fertilizers, industrial solvents, detergents, synthetic hormones, pharmaceuticals, and heavy metals like mercury and lead. All are present in measurable levels in soils, waters, and even rainfall. This phenomenon, known as the invisible toxic rain, is a modern occurrence where artificial molecules travel with water vapor and fall over forests, lakes, and cities, subtly and cumulatively altering ecosystem composition. This leads to what ecologists call invisible extinctions, the slow death of little-known organisms such as amphibians, insects, fungi, soil bacteria, and underground species. Because these creatures aren't charismatic, don't appear in environmental campaigns, and aren't targeted by public policy, their extinction occurs without protest, without mourning, without record. Yet they are the ones keeping the world functioning, decomposing matter, pollinating plants, fertilizing soil, purifying water, and regulating atmospheric gases. Pollution also affects symbolic species, such as whales, polar bears, and seabirds. Tissue analyses of these species reveal high levels of polychlorinated biphenyls, PCBs, phthalates, dioxins, and other hormonal compounds, which interfere with their reproduction and development. Many stranded whales have stomachs full of plastic. Many seabirds feed their chicks bottle caps, lighters, and toy fragments, mistaking them for floating prey. Death by starvation and intoxication has become common. Another aspect of modern pollution is noise, an invisible yet powerful contaminant. In the oceans, the sounds of ships, sonars, and extraction platforms disrupt cetaceans' navigation systems, leading whales and dolphins to beach themselves on distant shores. In cities, constant noise affects urban birds, causing them to alter their songs, breeding times, and even feeding behavior. Artificial light, in turn, disorients insects, sea turtles, and bats, disrupting natural cycles of life and death. Little by little, we are creating an inhospitable environment for life in all its forms. This is not just about excess trash. It's about a silent and continuous infiltration of substances and stimuli that unbalance the planet's ecological homeostasis. A chemical, sensory, and metabolic collapse that affects everything from soil bacteria DNA to the human brain. At its core, invisible extinctions mirror modernity itself. Fast, fragmented, globalized, and silent. The big question is, how many more losses will we ignore before we realize we are poisoning ourselves from within? The classic image of Noah's Ark, carrying pairs of animals towards salvation through a great flood, evokes a powerful idea, preserving life's diversity against an impending collapse. But in our contemporary reality, that ark is sinking, and the passengers are vanishing. Not two by two, but in entire groups, ancient lineages, whole genera. This chapter takes us into one of the most dramatic and least understood aspects of the environmental crisis, the global loss of genetic diversity. Today, over 42,000 species are officially listed as threatened with extinction by the International Union for Conservation of Nature, IUCN. Among them, more than 9,000 are classified as critically endangered, the final step before total extinction. These include animals, plants, fungi, corals, and microorganisms surviving in ever-shrinking habitats, surrounded by roads, farmland, cities, or pollution. Each of these species carries unique genetic information, the result of millions of years of adaptation. When a species vanishes, that evolutionary library is lost forever. The loss of species isn't just about numbers. It represents the silent erosion of global genetic variability, the raw material of evolution. Every isolated population, every subspecies, every ecotype contains adaptive genes that may provide resistance to disease, climate change, soil variations, salinity, altitude, water scarcity, or predator abundance. By losing this variability, the planet also loses its capacity for ecological resilience. Species with small populations suffer from a phenomenon known as genetic depression. With few individuals to reproduce, there's a higher chance of inbreeding. This reduces genetic diversity, increases the presence of harmful genes, and weakens the population, making it even more vulnerable to diseases, infertility, lethal mutations, and extreme climate events. It's a spiral of genetic decline that often precedes biological extinction. Another critical factor is the speed of the loss. Whereas past extinction events occurred over thousands or millions of years, species today disappear in mere decades, or less. On average, a vertebrate species is declared extinct every 1 to 2 years. But this number is underestimated. Countless species vanish without ever having been described. It's estimated that over 80% of Earth's microbial biodiversity is still unknown, and many of those organisms may have already been lost in degraded regions before we even knew they existed. Genetic loss also threatens food security. Today, over 75% of the world's food supply comes from just 12 plant species and 5 animal species. This genetic homogenization makes the global food system extremely vulnerable to pests, climate change, and disease. Local varieties of maize, rice, potatoes, and wheat, adapted to specific soil, altitude, and climate conditions, are disappearing as standardized commercial seeds replace traditional crops. When a disease strikes one of these monocultures, there's not enough genetic diversity to contain the catastrophe. The same holds true for domesticated animals. Traditional breeds of cattle, sheep, pigs, and chickens, bred for centuries by local communities, are being replaced by industrial lineages. This represents not only a loss of culture and knowledge, but also a shrinking genetic base needed to face new health or climate threats. There are efforts to reverse this trend. Genetic banks, such as the Svalbard Global Seed Vault in Norway, store millions of seeds in underground vaults to safeguard agricultural diversity. Conservation programs aim to freeze semen, eggs, and tissue from endangered species. But these initiatives, while important, are palliative. They cannot replace functional habitats, living ecological interactions, and wild populations in harmony with their environment. The truth is that it's not enough to save an animal's DNA in a lab. We must save the environment it lives in, the cycles that sustain it, the pollination partners, the natural predators, the rhythm of the seasons. The genetic code is only one part of the whole, and the whole is collapsing. When we think of extinction, we imagine the end of a species, but before that comes functional extinction, ecological extinction, and genetic extinction. Each of these stages weakens life in imperceptible ways, and like all slow erosion, we only recognize the abyss when it's too late. Understanding the history of mass extinctions would be impossible without the sciences that study the Earth's deepest traces, and among them, paleontology holds a central role. It allows us to reconstruct entire eras from fragments, a mineralized bone, a fossilized shell, the imprint of a leaf, the mark of a footprint. Each fossil is like a preserved sentence from a book that was almost entirely burned, and the mission of paleontologists is to recreate that book with precision, patience, and science. Modern paleontology combines field excavation with cutting-edge laboratory analysis. The geological layers of Earth's crust function as a vast natural archive where time is stacked in sediment. Deeper rocks are older, higher layers reveal more recent periods. Within these layers lie fossils that indicate the presence of life, its transformations, its abundance, and most importantly, its collapses. Mass extinctions typically leave a clear signature in this record, an abrupt break in fossil diversity, accompanied by chemical and physical changes. This is how scientists identified the end of the dinosaurs. At the transition between the Cretaceous and Paleogene periods, there is a global thin sediment layer rich in iridium, an element rare in Earth's crust, but common in asteroids. This layer aligns with the timing of the Chicxulub impact. Alongside it are traces of volcanic ash, melted glass spheres, sudden declines in fossil diversity, and the disappearance of numerous organisms. This collection of evidence, corroborated by radiometric dating, confirmed one of the greatest mass extinctions in history. Beyond macroscopic fossils, science now explores what is known as paleogenetics, the study of genetic material preserved in ancient remains. Thanks to advancements in ancient DNA extraction and analysis, we can now understand how certain lineages disappeared, what their genetic variations were, how they related to other species, and even how they endured extreme environments before going extinct. This technique has been successfully applied to mammoths, saber-toothed tigers, cave bears, and even extinct hominins like Homo neanderthalensis. Another crucial field is isotopic geochemistry. With it, scientists analyze the ratios of elements like carbon, oxygen, and sulfur in rocks to infer past climate changes, carbon cycles, and anoxic events, lack of oxygen. Variations in these elements can reveal, for instance, moments of ocean acidification, intense volcanism, or solar radiation blockages. Each piece of data expands our understanding of the context in which life either flourished or was abruptly halted. Mass extinctions also left their mark in fossil microorganisms, such as foraminifera and diatoms. Due to their abundance, variety, and sensitivity to environmental change, these organisms are excellent bioindicators. Their fluctuations in abundance and diversity across geological records provide a precise chronology of global ecological stress events. Many major extinctions are first identified by sudden drops in microfossil diversity. But it's not only the past that matters. The science of extinction has become a tool for predicting the future. Computational models combine paleontological, ecological, climatic, and genetic data to project possible scenarios in the face of today's crisis. These models simulate species behavior under environmental stress, ecosystem collapses, the loss of ecological services, and tipping points. In other words, Earth's deep history is being used to try to prevent a catastrophic future. Modern genetics plays a vital role in this effort. By mapping the genomes of endangered species, scientists identify the levels of genetic diversity, isolated populations, inbreeding risks, and adaptive potential. This enables more effective conservation strategies, such as targeted breeding, reintroductions into natural habitats, and the creation of ecological corridors. But it also raises ethical and scientific dilemmas about how far we should intervene. The boundary between conservation and manipulation is being tested with technologies like CRISPR and cloning. Projects are already underway to revive extinct species, such as the passenger pigeon, the thylacine, and the woolly mammoth, using genetic engineering and genome editing. But even if we succeed in bringing them back, will they have a world to live in? Or will they be mere scientific trophies from a destroyed past? What paleontology, genetics, and fossils teach us, ultimately, is that life on Earth is resilient, but not infinite. Extinctions have left deep scars, and science is the scalpel that reveals them. It is up to us, with this knowledge in hand, to decide whether we will repeat the mistakes of the past, or write a new and more conscious chapter in the long history of life. Knowing that there were 5 major mass extinctions, identifying the exact moment dinosaurs vanished, reconstructing the climate from 250 million years ago, understanding when an ocean dried up, when a forest turned into coal, or when a volcano drowned the planet in ash. All of this and much more now is possible thanks to a science that deciphers time, not with clocks, but with layers. Stratigraphic geology. This section explores the scientific method behind reading Earth, turning rocks into witnesses of deep time. Planet Earth is like an immense book written in stone, where each page is a geological layer. These layers, called quantistrata, form over thousands or millions of years through the slow deposition of sediments, sand, mud, volcanic ash, dissolved minerals, organic remains. As time passes, these layers compact and become sedimentary rocks. Within them are preserved fossils, minerals, crystals, and chemical signatures that reveal what the world was like when they formed. Reading these layers is called stratigraphy. It forms the basis of paleontology, geochronology, and the reconstruction of events such as extinctions, ice ages, and global climate changes. The most important rule is known as the principle of superposition. Deeper layers are older than the ones above. This simple principle allows us to chronologically organize Earth's history, even without absolute dates. But how do we determine the exact age of a layer? The answer lies in cell radiometric dating. Elements like uranium, potassium, and carbon have unstable isotopes that decay into other elements at a constant rate, like an atomic hourglass. By measuring the ratio between the original isotope and its final product, scientists can calculate the rock's age with precision, down to millions or even billions of years. This technique enabled us to date events like the Chicxulub impact 66 million years ago, the Siberian Traps eruptions, 252 million years ago, and the beginning of the Ice Age, 2.6 million years ago. Beyond dating, geologists use index fossils, species that lived for short periods but spread widely across the planet. Finding such fossils in different parts of the world allows scientists to correlate distant layers and establish a global chronology. This was crucial for identifying the Cretaceous-Paleogene boundary, dinosaur extinction, and many other events. The layers also contain chemical signatures that reveal abrupt changes. For example, an abnormal presence of iridiums in a layer may indicate an asteroid impact. A sulfur spike suggests intense volcanism. Variations in carbon and oxygen isotopes show global temperature changes, ocean acidity, and even atmospheric oxygen levels. In many cases, these signatures coincide with sharp drops in fossil diversity, forming what are known as extinction boundaries. Some layers are so distinct they've become global markers. The iridium-rich layer from 66 million years ago is one. Another is the carbon-rich black shale from the late Devonian, linked to oceanic dead zones. There are also layers filled with volcanic ash, like those left by the Deccan Traps eruptions. And more recently, we can already identify modern layers containing coplastics, industrial metals, radioactivity, and synthetic pollutants, clear signs of human presence in the geologic record. These modern layers lead to the proposal of a new geological epoch, the Anthropocene. Still debated among scientists, this new era would mark the beginning of humanity's planetary-scale impact. Possible markers include the onset of nuclear testing, the global spread of plastics and pesticides, ocean acidification, and accelerated species loss. If confirmed, the Anthropocene would become the layer of the present and of warning. Reading geological layers is therefore in a long-duration testimony. It allows us to see beyond our human timescale, to identify patterns, predict risks, and understand the slow, yet relentless rhythms of planetary history. Each layer holds the record of an entire world that once existed, thrived, and disappeared. And with every new excavation, we learn more about what we once were and what we may cease to be. The question may sound philosophical, even poetic. Does the Earth learn? But behind this provocation lies a deep foundation in biology and geology. The understanding that the history of life is not just a sequence of random events. It is also a process of experimentation, adaptation, selection, and resilience. Every mass extinction left its marks, and every biological rebirth brought surprising innovations. In this section, we reflect on what Earth's billions of years can teach us, not as metaphors, but as concrete warnings. Over the last 4.5 billion years, the planet has undergone countless transformations. The oxygen we breathe today exists only because cyanobacteria, billions of years ago, learned to perform photosynthesis. The continents were once united, Pangaea, and later drifted apart. Entire oceans disappeared. Glaciations swallowed nearly the whole planet. Meteors tore through the sky and redrew the continents. Volcanoes erupted for hundreds of thousands of years, and life, despite all of this, persisted. Every mass extinction represented a brutal break in the course of evolution, and at the same time, it opened space for novelty. When trilobites vanished at the end of the Permian, the ancestors of dinosaurs emerged. When dinosaurs disappeared at the end of the Cretaceous, mammals exploded in diversity. Life is creative, and time is its laboratory. What changes with each event is the cost. The more abrupt the change, the higher the ecological price. In Earth's history, it's possible to observe a pattern of cycles: crisis, extinction, rebirth, diversification. But it's also possible to see a process of increasing complexity. The first organisms were unicellular, then came multicellular ones, then organisms with tissues, organs, systems. Eyes evolved more than 40 times in different lineages. Wings appeared in insects, birds, and gliding mammals. Intelligence arose in mammals, octopuses, birds, life experiments, and some of these paths lead to consciousness, culture, language. This progression is neither linear nor guaranteed. Each extinction can sever entire branches of the tree of life. Many evolutionary innovations arose only once, and if lost, they may never reappear. One example is reef-building corals, which evolved very few times and may disappear due to ocean acidification. Another is the adaptive immune system of vertebrates, an innovation that emerged hundreds of millions of years ago and underpins our ability to survive viruses and bacteria. These are deep, irreplaceable inheritances. What Earth shows us in retrospect is that life is resilient, but not invulnerable. Mass extinctions always took millions of years to be offset. The most severe of all at the end of the Permian took over 10 million years to restore marine diversity. In other words, even when life resurfaces, it does so slowly, on a timescale beyond ours. There's a hard lesson here. If we cause a global collapse now, the Earth may indeed recover, but we may no longer be here to witness it. Recovery could take tens of millions of years. Human civilizations, cultures, languages, cities, technologies, all could disappear without leaving successors. The planet would carry on, but not with our version of life. On the other hand, we are the first known species capable of understanding extinctions before they happen. We have telescopes that see galaxy formation, microscopes that observe viruses, supercomputers that simulate future climates. We have the geological memory of the past, the genetic capacity to foresee population collapses, the knowledge needed to interrupt cycles of destruction. Never before has an animal had so much information to choose the future it wishes to build. The question, does the Earth learn, might need to be flipped. Do we learn from the Earth? Can we look at past patterns and change our path? Can we see in past extinctions not just curiosities, but warnings? Can we ultimately position ourselves as part of the biosphere, and not as its rulers? Geological time is patient, but it is also ruthless with those who defy it without humility. And what it teaches us, in silence, is that all arrogance ends up in the sediment. Over billions of years, Earth has been shaped by geological forces, colossal asteroids, continental volcanoes, catastrophic glaciations, and sudden atmospheric shifts. But none of these forces, until now, had ever been conscious. None possessed language, technology, maps, science, religion, or the ability to deliberately alter the chemical composition of the atmosphere. That is, until Homo sapiens appeared. And with humanity came a new chapter in the history of life, the Anthropocene, the geological age of human influence. The term Anthropocene is not merely a metaphor, it is a scientific concept increasingly accepted by geologists, ecologists, climatologists, and paleontologists. It proposes that human activity has already left such a deep and lasting impact on Earth's systems that it will be detectable in future geological records, like a new layer, distinct from those caused by volcanism or asteroid impacts. This new epoch is believed to have begun around the second half of the 20th century, marked by an unprecedented planetary accelerator. Since then, all curves of human impact have taken the shape of exponential explosions. Population growth, greenhouse gas emissions, deforestation, fertilizer use, plastic production, species extinctions, urbanization, ocean acidification, soil loss, and large-scale mining. Every decade, we double or triple the pressure on living systems. With each generation, we cross planetary boundaries that regulate the ecological stability of the Earth. The Anthropocene is not just an age of change, it is an age of rupture. We are disrupting the global water cycle through dams, intensive irrigation, and glacier melt. We are destabilizing the planet's thermal balance through the massive release of carbon dioxide and methane. We are turning entire tropical forests into pasture and soybean fields. We are covering continents in concrete and cities. We are exterminating species before we even know they exist. And all of this has happened in less than 300 years since the Industrial Revolution. The cumulative impact is already comparable to the great extinction events of the past, but with a brutal difference. We are both the asteroid and the dinosaurs. We are simultaneously the destructive force and the victims of the destruction. Global warming caused by fossil fuel combustion is pushing the planet to temperature levels not seen in over 3 million years. Polar glaciers are melting. Sea levels are rising. Extreme events are multiplying. Ecosystems are collapsing. Diseases are spreading. And biodiversity is retreating in the face of urbanization, fire, pollution, and greed. At no other point in history Has a single biological group had the power to change the atmosphere's composition, exhaust the oceans, alter the planet's albedo, and trigger the sixth mass extinction? We are that force. And unlike an asteroid, we can choose. We can mitigate, restore, preserve, or continue accelerating toward the abyss. The Anthropocene has already left its mark in modern sediments. Layers with plastic, industrial ash, heavy metals, radioactive particles from nuclear tests, fossils of domesticated animals, and genetically modified plants. These will be the fossils of the future. When millions of years from now another being excavates today's rocks, they will find a thin, dark layer filled with signs of collapse, and perhaps of learning. The Anthropocene doesn't have to be only the age of destruction. It can also be the age of ecological consciousness, the age in which the dominant species, for the first time, recognized its role in the web of life and chose to change. To change its economy, its relationship with nature, its way of consuming, producing, and inhabiting the planet. To change out of ethics, empathy, survival. But time is short. We are crossing points of no return. In the Amazon, the polar ice sheets, the coral reefs. Every year without action is a decade lost. Every forest destroyed is a burned chapter of the Earth's living memory. Every species that goes extinct is a new silence in the planet's song. In the end, the Anthropocene will not be judged by geology alone. It will be judged by the moral history of our species. We had all the tools: science, data, models, satellites, accumulated knowledge. We knew. And the question that remains is, what did we do with that knowledge? Even among the most tragic events in the history of life, there are curious, counterintuitive, and even fascinating facts that reveal the complexity of these cycles of death and rebirth. Mass extinctions were not merely annihilations. They were also gateways to the unknown, laboratories of evolution, and chapters full of exceptions. This section highlights some of the most surprising discoveries science has made while investigating the times when the world nearly ended. To begin with, it's intriguing to know that extinctions do not affect all organisms equally. During the Permian collapse, the largest of all, more than 90% of marine species had disappeared. Yet certain types of bacteria thrived. Anaerobic microorganisms, which live without oxygen, colonized dead oceans, and even influenced the climate by releasing large amounts of methane. What was an end for many became a feast of opportunity for others. Another curious fact involves dinosaurs. The famous extinction that ended their reign 66 million years ago did not kill all dinosaurs. The birds we know today are actually adapted theropod dinosaurs. That is, the pigeon in the square, the rooster on the farm, and the hummingbird in the garden are direct descendants of fearsome raptors and tyrannosaurs. This lineage survived because, among other reasons, it was smaller, had a more efficient metabolism, and relied less on large prey. During the late Devonian extinction, which spanned millions of years, something even more surprising occurred. Most of the extinctions happened in cycles, not abruptly. Biodiversity declined gradually, in pulses spaced hundreds of thousands of years apart. This suggests that prolonged environmental instability, like climate fluctuations and changes in sea level, can also lead to collapse, even without catastrophic impacts. In the Ordovician-Silurian event, one hypothesis is that the extinction was not caused by heat, but by extreme cold. The snowball Earth theory suggests that the planet nearly froze over, covering oceans with ice even in the tropics. This sudden cooling would have dropped sea levels and wiped out much of marine life. It's a powerful reminder that life depends on delicate thermal balances. Too much heat or cold can be equally fatal. Some extinctions also revealed curious size survival patterns. In the Cretaceous-Paleogene event, for example, most land vertebrates over 25 kilograms went extinct, but small mammals, reptiles, and birds managed to survive by hiding in burrows, holes, or adapting to alternative food sources. This shows that in times of crisis, being small can be more viable. Other organisms survived through even more ingenious strategies. Some bony fish from the Devonian developed primitive lung capacity, allowing them to survive in low oxygen environments. Certain marine animals during the Permian extinction survived by migrating to deeper ocean zones, where conditions were more stable. In many cases, ecological flexibility was the trump card that saved entire lineages. Curiously, Earth itself seems to have a cyclical rhythm of extinctions. Studies suggest that major biodiversity losses occur every 26 to 30 million years. The cause is unknown, but some hypotheses involve under-orbital oscillations of the solar system, passage through interstellar clouds, or galactic activity that disturbs Earth cyclically. If these patterns are real, we may be living at the end of one such interval, coinciding with the current ecological crisis. Among the most intriguing findings are also cases of mistaken fossils. For decades, scientists believed certain species had vanished millions of years ago, until they were found alive. A classic example is the coelacanth, a prehistoric fish thought to be extinct since the Cretaceous, but caught alive in the 20th century off the coast of Africa. These species are called living fossils, and they represent the ghost lineages that survived in the silence of the deep. Even post-extinction recovery brings surprises. After the Permian event, new life forms emerged with the experimental morphologies. Reptiles with unusual crests, giant amphibians, predators with elongated snouts, herbivores with internal bony plates. It's as if evolution, faced with emptiness, tested unprecedented forms until balance was restored. Mass extinctions are simultaneously tragedies and catalysts. They are the memory of collapse, but also the source of innovation. And the more we learn about their details, the more we understand the incredible complexity that shapes the planet we inhabit. There is something deeply moving in the idea that Earth, this rocky planet spinning around an ordinary star in a galaxy among billions, has already witnessed 5 great endings. Each one erased entire worlds, reshaped oceans, turned forests into ashes, and silenced voices we will never hear. And still, life endured, silent, fragile, reinvented, persistent. In this final section, we reflect on what extinctions teach not only science, but at the human spirit in the face of eternity. The first lesson is that of impermanence. No form of life, no matter how dominant, magnificent, or widespread, is eternal. Trilobites ruled the seas for 270 million years and vanished. Dinosaurs, sovereigns for 160 million years, succumbed within weeks. Corals, forests, giant birds, massive predators, all had their days of glory and of silence. This places our own existence in perspective. Human time is a breath between abysses. The second lesson is that of interconnection. Every mass extinction began as a chain of seemingly isolated events: a super-eruption, a change in sea level, the impact of an asteroid, the rise of a new dominant lineage. But no collapse was ever local. All of them spread, intensified, became global. This proves that everything is connected. The oxygen from one forest feeds the coral on the other side of the planet. The collapse of insects impacts birds, seeds, climates. We are part of an interwoven system, and each torn thread reverberates through the whole. The third lesson is that of silent innovation. Life not only resists, it reinvents itself. With each extinction, Earth tested new paths. From darkness came eyes. From dry land came wings. From death came music. The creative power of evolution is an ode to the unknown. And it reminds us that even when everything seems lost, the invisible is germinating, preparing the next act, the next biological miracle. But perhaps the most urgent lesson is that of limits. Earth can regenerate, but it needs time. Time that may be geologically brief, but biologically devastating. After the Permian event, biodiversity took more than 10 million years to recover. This means that if the current 6th extinction runs its course, there will be no redemption for centuries, nor for millennia. The natural systems that support our civilization, stable climate, clean water, fertile soil, pollinators, productive seas, may vanish in real time. And Homo sapiens, no matter how intelligent, cannot survive outside the web it destroyed. The eternity of life is no guarantee for any species. The planet will continue, but the life forms that surround us today, the songs, the flavors, the behaviors, the bonds, all of this could become fossils. And one day, it may be read by another consciousness, or by no one at all. And yet, The fact that we are here now, reflecting on this, is a miracle. Never before in Earth's history has a species been able to look at mass extinctions and say, we know. We know how it starts. We know where it leads. We know what to do. We are the only chance the biosphere has to avoid the abyss with awareness, and that responsibility is perhaps humanity's greatest gift and greatest burden. Eternity does not belong to us, but choice does, and as long as there are trees, seas, clear skies, free species, untouched seeds, and children who listen to the wind, life still has something to say. May we be able to hear it. May we be worthy to continue.